Welcome to the Midnight Lesson. Tonight's journey stretches beyond imagination, beyond distance, beyond even the limits of human comprehension. As the world grows quiet around you, as the day releases its final thoughts and the night settles in, we begin a voyage outward. Farther than any road, deeper than any ocean, and older than any story ever told. If you have topic ideas you would like to see explored in future Midnight Lessons, place them in the comments below. Your curiosity helps guide these journeys. Now dim the lights, relax your eyes, and allow the universe to unfold. Because tonight, we explore the 10 largest things in existence. Not the largest animals, nor the largest planets, nor even the largest stars alone. We move beyond those familiar giants into structures so vast, they reshape how we understand reality itself. Objects so immense that light takes millions, even billions of years, just to cross them. Realms where distance is measured not in miles or kilometers, but in epochs of time. To understand the largest things, we must first understand scale. Human beings evolved to understand the world at walking speed. We measure distance in steps, in miles driven, in hours flown. Even our greatest planetary journeys remain small in cosmic terms. The Moon, our closest celestial neighbor, is about 238,000 miles away. A vast distance to us, yet in cosmic scale it is nearly touching Earth. Light, the fastest thing in the universe, travels that gap in just over 1 second. From there, our sense of size begins to break. The Sun, for example, could fit about 1.3 million Earths inside it. Already the mind strains to visualize such immensity, and yet the Sun is considered an average star. There exist stars so large that if placed where our Sun sits, their outer layers would swallow the orbits of Jupiter, Saturn, even Uranus. But even those stellar titans are small compared to what lies ahead, because stars gather. They form clusters. Clusters gather into galaxies. Galaxies gather into groups, groups into clusters, clusters into superclusters, and superclusters into vast filaments that stretch across the observable universe like glowing strands of a cosmic web. When astronomers map the universe at its largest scale, it does not look random. It resembles neurons in a brain, or foam bubbles pressed together, or the delicate threads of a spider's web glistening in darkness. Between these filaments lie enormous voids, regions so empty that a traveler could cross millions of light years without encountering a single galaxy. Silence on a scale so complete it defies language. So when we ask what the largest things in the universe are, we are not speaking only of size. We are speaking of structure, of gravity's grand architecture, of how matter itself arranges across billions of years. Our journey tonight will move step by step outward through this hierarchy of immensity. We will begin with objects already beyond comprehension. Stellar giants that dwarf our solar system. Nebulae so vast they give birth to thousands of stars at once. Molecular clouds spanning light years like cosmic oceans of gas and dust. From there we expand into galaxies, island universes containing hundreds of billions of stars each. Spirals, ellipticals, irregular swarms of light bound by gravity and time. But galaxies do not drift alone. They gather into clusters, gravitationally bound cities of galaxies, each member orbiting a shared center of mass. These clusters collide, merge, and warp spacetime itself through their combined gravity. Beyond them lie superclusters, structures so large they were once thought to be the ultimate organization of matter. But even they are not the end. Modern surveys of the cosmos reveal something even greater. Galactic filaments stretching billions of light years. Walls of galaxies forming boundaries around titanic voids. Structures so large that some challenge our understanding of how the universe formed at all. And at the farthest edge of our list lie the true giants, the largest known structures in existence. Objects so vast that naming them feels inadequate, where size is measured not only in distance, but in the fraction of the observable universe they occupy. As this journey concludes, the scale of existence itself may feel different. You may look at the night sky and no longer see scattered stars, but pieces of something larger, threads in a vast cosmic tapestry still expanding, still evolving, still moving toward futures we cannot yet witness. But before we reach those unimaginable extremes, we must ground ourselves in perspective. Consider this. If Earth were the size of a grain of sand, the Sun would be a large marble about a meter away. Jupiter would be a peppercorn several meters farther out. Pluto, a speck at the edge of a large room. Now expand the model. To include the nearest star, Proxima Centauri, you would need to place another marble thousands of miles away. The solar system, in this scale, vanishes into insignificance. And yet, even that expanded distance is microscopic compared to the structures we will soon encounter. Because the universe does not merely contain large things, it contains layers of largeness, each scale built upon the one before it, each governed by gravity, time, and the slow sculpting of cosmic evolution. Tonight's lesson is not simply about size, it is about humility, about perspective, about understanding where we exist within this vast hierarchy. From the surface of Earth, our concerns feel immense. Cities feel large, mountains feel eternal, oceans feel boundless. But from the vantage point we are about to take, Earth itself disappears, the Sun becomes a spark, our galaxy a swirl of dust, and still we continue outward. So settle in, let the breathing slow, let the mind drift as we begin with the first of the great giants. The journey to the largest things in the universe begins not at the edge, but with a titan that already defies comprehension. A star so large that if it replaced our Sun, its surface would extend beyond the orbit of Saturn. A stellar colossus whose volume could contain billions of suns. Our first step into immensity begins there. Chapter 1. The Stellar Titan. To begin our ascent into the largest known structures in existence, we start with something that, on its own, already overwhelms comprehension. A single star. But not just any star, a hypergiant. A stellar titan so vast that it stretches the very definition of what a star can be. In the quiet darkness of the constellation Scutum, roughly 9,500 light-years from Earth, resides one of the largest stars ever discovered. A red hypergiant whose name, while clinical in catalogue form, barely captures its enormity. Scuti, if placed at the center of our solar system, where the Sun now burns, its outer atmosphere would extend beyond the orbit of Jupiter. Some estimates place its radius reaching toward Saturn's path. To understand this, the mind must abandon ordinary comparison. The Sun's diameter is about 864,000 miles, already vast beyond intuitive grasp. Scuti's diameter is estimated to be roughly 1.5 billion miles. If Earth were the size of a marble, the Sun would be a beach ball. Scuti, by comparison, would be a mountain. But diameter alone does not tell the full story. Volume reveals the true scale. Roughly 5 billion suns could fit inside Scuti. 5 billion stellar furnaces, each capable of sustaining solar systems, each containing more mass than all planets combined. And yet they would vanish inside this single star. If a commercial jet attempted to fly around Scuti at typical cruising speed, roughly 550 miles per hour, the journey would take over 3,000 years without stopping. Even light, moving at 186,000 miles per second, would require hours to circle its circumference. But size at this scale introduces instability. Hypergiants live fast and die violently. Their immense gravity compresses their cores to extreme pressures, accelerating nuclear fusion far beyond the steady pace of stars like our Sun. Where the Sun may burn for 10 billion years, hypergiants exhaust their fuel in mere millions. Scuti is nearing the end of its life. Its outer layers pulse and expand, shedding vast shells of gas into space. These ejections form nebulae that will one day seed new stars, new planets, perhaps even new life. So even in death, giants give birth. But Scuti is not alone among stellar titans. Another rival exists in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, WOG 64. Another red hypergiant, shrouded in thick clouds of expelled dust and gas. Its true size is difficult to measure precisely because its atmosphere blends into the surrounding nebula, like fog dissolving into night. Some measurements suggest it rivals or exceeds Y Scuti at certain wavelengths of observation. And beyond these lies Stephenson 2-18, often considered one of the largest known stars by radius. If placed in our solar system, its photosphere would engulf the orbit of Saturn entirely. Imagine looking up from Earth and seeing the sky filled edge to edge with a dull red surface. No stars visible, no darkness. Only the churning atmosphere of a star so vast it replaces the heavens. But here is where perception shifts again. Despite their enormous size, hypergiants are not the most massive stars. Many are relatively low density. Their outer layers are bloated, extended by radiation pressure and late-stage fusion processes. They are, in a sense, cosmic foam, vast but diffuse. If you could scoop material from their outer atmosphere and bring it to Earth, it would be thinner than the best vacuum ever created in a laboratory. Size does not always mean weight. Still, their luminosity defies comprehension. Y Scuti shines hundreds of thousands of times brighter than the sun. From thousands of light years away, it remains visible to telescopes as a brilliant ember against the galactic dark. But brightness at that distance conceals the true violence occurring within. Deep in its core, fusion chains heavier elements. Hydrogen long exhausted, helium burned through, carbon and heavier nuclei forming in nested shells like layers of an onion. Each fusion stage grows shorter, each more unstable, until iron forms. Iron fusion does not release energy. It consumes it. When enough iron accumulates, the outward pressure that holds the star up collapses. Gravity wins. In less than a second, the core implodes, then rebounds. The resulting supernova can briefly outshine an entire galaxy. Shockwaves rip outward, tearing the star apart, forging heavy elements like gold, uranium, and platinum in the explosion's fury. Every atom of gold on Earth was born in such a death. So when we observe hypergiants, we are witnessing not only scale, but inevitability. They are cosmic time bombs. Beautiful, temporary, doomed. Yet even these stellar leviathans are small compared to what lies ahead. Because stars rarely form alone, they emerge from stellar nurseries, vast molecular clouds spanning dozens, sometimes hundreds of light years. Regions where gravity gathers gas and dust into knots that ignite nuclear fire. To grasp the scale difference, consider this. If Y Scuti were reduced to the size of a grain of sand, the molecular cloud that birthed it would be the size of a continent. Stars, even the largest, are merely sparks within much larger structures. But before we leave the realm of individual stars, one more perspective anchors their enormity. Sound cannot travel through space. There is no air to carry vibration. But if it could, if interstellar medium were dense enough, the surface of a hypergiant would roar beyond imagination. Convection cells the size of solar systems churn slowly across their surfaces. Plasma rises, cools, and sinks in cycles lasting years. Solar flares dwarf planetary orbits. Shockwaves ripple through their atmospheres like storms on a scale no world could survive. And yet, from Earth, they appear as faint points of light, tiny, distant, silent. This contrast defines cosmic scale. The largest things often look the smallest from afar. And as our journey continues, that illusion will only deepen, because the next step outward dwarfs even hypergiants. We move from single stars to the colossal stellar nurseries that create them. Regions of space so vast, so dense with raw material, that thousands of suns can ignite within them. Realms where gravity sculpts light itself, where the largest stars are born, and where size begins to transcend individuality entirely. Chapter 2. The Birth Oceans of Stars. Before a giant star can exist, before hypergiants swell to unimaginable radii, Before fusion ignites and light floods the darkness, something even larger must come first. A stellar nursery, a molecular cloud, an ocean of raw creation drifting silently through the galaxy. These clouds are among the largest coherent structures made primarily of ordinary matter. Vast regions composed mostly of hydrogen molecules, threaded with helium, dust, trace elements, and complex organic compounds. They are cold, so cold that temperatures fall to just 10 degrees above absolute zero. At these extremes, atoms move slowly. Collisions are gentle. Light struggles to penetrate the dense dust lanes woven through the cloud's interior. From afar, they appear as dark stains against the bright river of the Milky Way. But inside them, creation unfolds. One of the most famous stellar nurseries visible from Earth lies in the constellation Orion, the Orion Molecular Cloud Complex. Stretching over 1,500 light-years, this immense structure contains enough material to form hundreds of thousands of stars. To place that scale in perspective, if our entire solar system were placed inside this cloud, it would vanish without trace, lost like a grain of sand in a planetary ocean. Within this complex lies the Orion Nebula, a glowing cavity carved by newborn stars. Ultraviolet radiation from these young suns ionizes surrounding gas, causing it to shine in brilliant hues of red, violet, and blue. But the visible nebula is only a small blister on the surface of a much larger structure. The true giant is the cold molecular cloud surrounding it, invisible to human eyes, revealed only through radio and infrared telescopes, capable of detecting faint emissions from carbon monoxide and other tracer molecules. Inside these clouds, gravity begins its slow work. Tiny density fluctuations form. Regions slightly heavier than their surroundings begin pulling in more gas. Over millions of years, these knots collapse inward. As they compress, temperature rises. Pressure builds. Eventually, the core becomes hot enough to ignite hydrogen fusion. A star is born. But molecular clouds do not create just one star at a time. They create thousands. Entire clusters ignite within the same cloud, illuminating it from within like lanterns in fog. Consider the Carina Nebula, another stellar nursery within our galaxy. Over 300 light-years across, it contains some of the most massive stars ever observed, including Eta Carinae, itself a hypergiant system nearing catastrophic eruption. Jets of plasma blast from newborn stars at hundreds of kilometers per second. Shockwaves ripple through surrounding gas, compressing new regions and triggering further star formation. Creation begets creation, a chain reaction spanning light years. But even Carina is modest compared to the largest molecular clouds known. The Tarantula Nebula, located in the Large Magellanic Cloud, is the most active star-forming region in the local group of galaxies. If it were as close to Earth as the Orion Nebula, it would cast visible shadows at night. At its core lies R136, a dense star cluster packed with some of the most massive stars ever discovered, many exceeding 100 times the Sun's mass. Radiation pressure from these giants sculpts the surrounding gas into pillars, caverns, and shock fronts. The cloud glows not softly but violently, a furnace of ultraviolet light and stellar wind. Yet even the Tarantula Nebula is only a fragment of its parent molecular complex, because the largest molecular clouds are not merely nebulae, they are galactic structures. Take, for instance, the Sagittarius B2 cloud near the center of the Milky Way, a colossal molecular reservoir containing the mass of several million suns. It spans roughly 150 light-years and contains some of the richest chemical complexity ever observed in space. Astronomers have detected alcohols, aldehydes, glycolaldehyde, and other prebiotic molecules within it, the building blocks of life adrift in cold darkness. If Earth's entire biosphere were vaporized and dispersed, its organic inventory would still be insignificant compared to the chemical wealth inside Sagittarius B2. But scale expands further still. The largest known molecular structures are giant molecular clouds, or GMCs. These titans can span 300 light-years and contain up to 10 million solar masses of material. One example, the W51 cloud complex, is among the most massive star-forming regions in the Milky Way. Its dense cores collapse into clusters while supernova shockwaves from earlier generations compress new regions into ignition. Stars are not born quietly here. They are born in storms. Supersonic turbulence ripples through the gas. Magnetic fields twist and knot. Radiation pressure carves cavities large enough to swallow solar systems whole. Inside these clouds, darkness and brilliance coexist. Regions so opaque that even infrared light struggles to escape lie beside cavities blazing with newborn stars. To travel through such a cloud would be disorienting beyond imagination. At times the sky would blaze with hundreds of nearby suns. At others it would fall into pitch blackness as dust blocked all starlight. Distances between forming stars would still measure trillions of miles, yet compared to the emptiness between mature stars, it would feel crowded. But the largest stellar nurseries are not confined to our galaxy. In starburst galaxies, molecular clouds reach even greater extremes. Galaxies undergoing intense star formation compress vast reservoirs of gas into dense regions where stars ignite at rates hundreds of times faster than in the Milky Way. Clouds merge, collapse accelerates. Clusters form containing millions of stars. These environments may resemble conditions in the early universe, when galaxies were richer in cold gas and star formation raged more violently. In such epochs, molecular clouds may have grown to scales rarely seen today, precursors to the largest stellar populations ever assembled. And yet, even these vast birth oceans are still substructures within something larger. They drift inside galaxies, carried along spiral arms like foam on galactic tides. From afar, molecular clouds appear as dark veins threading luminous star fields. They are the wombs of galaxies. Without them, no stars would form, no planets would coalesce, no chemistry would evolve toward biology. They are quiet architects of cosmic evolution, but they are temporary. Radiation from the stars they create eventually tears them apart. Stellar winds disperse gas. Supernovae blast shockwaves through their cores. What took tens of millions of years to assemble can be dispersed in a fraction of that time. Creation contains the seeds of its own destruction, yet even in dispersal, they enrich the galaxy. Heavy elements forged in stars mix into surrounding gas, seeding future clouds with richer chemistry. Each generation builds upon the last, a slow cosmic inheritance. But now, as our journey continues outward, scale shifts once more, because molecular clouds, vast as they are, remain small compared to the structures that contain them. They are eddies within spiral arms, clouds within galaxies, and galaxies themselves are the next step in our ascent toward the largest things that exist. Island universes of hundreds of billions of stars, each containing countless stellar nurseries like the ones we have just crossed, each separated by gulfs of space so immense that light requires millions of years to travel between them. As we leave the birth oceans behind, we approach the luminous cities of the cosmos, the galaxies, where scale expands from hundreds of light years to hundreds of thousands. Chapter 3. Galactic Cities of Light. Beyond the stellar nurseries, beyond the birth clouds where suns ignite and hypergiant swell, the scale of structure rises again. Stars do not scatter randomly through space. They gather, they orbit. They assemble into vast gravitational systems containing hundreds of billions of members. Galaxies. If stellar nurseries are oceans, galaxies are continents. Immense luminous cities of stars bound together by gravity, rotating through darkness over billions of years. Our home galaxy, the Milky Way, is one such structure. It spans roughly 100,000 to 120,000 light-years in diameter. Though newer measurements suggest its outer halo of stars and dark matter extends much farther, perhaps approaching 200,000 light-years. Inside it, 100 and 400 billion stars. Some small and dim, like red dwarfs that burn for trillions of years. others massive and short-lived, blazing intensely before dying in supernova explosions. Interspersed among them lie stellar remnants, white dwarfs, neutron stars, black holes, the collapsed cores of long-dead suns. The Milky Way is a barred spiral galaxy. Its structure includes a central bar-shaped concentration of stars, from which spiral arms extend outward like curved rivers of light. These arms are not rigid structures. They are density waves, regions where stars and gas crowd together as they orbit the galactic center. As gas enters these denser regions, it compresses, triggering star formation. This is why spiral arms glow with blue young stars and pink nebulae. They are stellar nurseries stretched across tens of thousands of light years. Our solar system resides in one of the smaller arms, known as the Orion Arm, or Orion Spur. We orbit the galactic center at roughly 515,000 miles per hour. Even at that speed, one full orbit takes about 225 to 250 million years. Since the dinosaurs went extinct, Earth has completed only a single galactic year. At the core of the Milky Way lies Sagittarius A, a supermassive black hole containing about 4 million times the mass of the Sun. It does not dominate the galaxy by size, but by gravitational influence within the central region. Stars near the core orbit it at extreme velocities, their paths mapped precisely through decades of observation. But the Milky Way, vast as it is not among the largest galaxies known. It is considered average. To grasp true galactic scale, we must look outward. One of the most famous nearby galaxies is Andromeda, also known as M31. Located about 2.5 million light-years from Earth, Andromeda is the largest galaxy in the local group, the gravitationally bound collection of galaxies that includes the Milky Way. Andromeda spans roughly 220,000 light-years in diameter. It contains perhaps 1 trillion stars, more than double the Milky Way's population. Its spiral structure is grand, its disk wide, its halo populated with ancient star clusters and streams of stars left behind by smaller galaxies it has consumed. Andromeda and the Milky Way are on a collision course. In about 4 to 5 billion years, the two galaxies will merge, not in a catastrophic spray of star collisions, as distances between stars are too vast for that to be common. Instead, gravity will reshape both galaxies, their disks will distort, tidal arms will stretch, and over billions of years they will settle into a single larger elliptical galaxy, a process already observed elsewhere in the universe. Galaxies grow not only by forming stars, but by merging with one another. Some galaxies reveal this history visibly. Centaurus A, for example, shows a dark band of dust slicing across a luminous elliptical body, evidence of a past merger between a spiral and an elliptical galaxy. But mergers are only one path to galactic enormity. Some galaxies formed large from the beginning. Consider IC 1101, one of the largest known galaxies. Located at the center of the Abell 2029 galaxy cluster, IC 1101 is a supergiant elliptical galaxy spanning roughly 4 million light-years in diameter. That is more than 30 times wider than the Milky Way. Its stellar population likely exceeds 100 trillion stars. If the Milky Way were reduced to the size of a coin, IC 1101 would be a large city. Elliptical galaxies like IC 1101 differ structurally from spirals. They lack defined arms. Instead, their stars orbit in three-dimensional distributions, forming smooth, spheroidal shapes. Many are ancient, containing older, redder stars, with little cold gas left for new star formation. They are, in a sense, galactic graveyards, the accumulated result of countless mergers. At the other end of the spectrum lie dwarf galaxies, small systems containing as few as a few million stars. The large Magellanic Cloud visible from the southern hemisphere is one such satellite galaxy orbiting the Milky Way. Though small compared to giants, dwarf galaxies are the most numerous type in the universe. They serve as building blocks in hierarchical galaxy formation models. Over cosmic time, larger galaxies grow by absorbing smaller ones. Streams of stars observed in the Milky Way's halo are remnants of such past mergers. But size is not measured by stars alone. Galaxies are embedded within halos of dark matter, invisible yet dominant in mass. Dark matter does not emit or absorb light, but its gravitational effects shape galactic rotation and structure. Measurements of star velocities show that galaxies contain far more mass than visible matter accounts for. The Milky Way's dark matter halo may extend over 1 million light-years, far beyond the luminous disk. In this sense, galaxies are larger than they appear. Their visible stars form only the bright cores of much larger gravitational domains. Gas also contributes to galactic scale. Hot ionized gas fills galactic halos, detectable in X-ray wavelengths. Cold hydrogen clouds drift between stars, forming reservoirs for future star formation. Magnetic fields thread through galactic disks. Cosmic rays stream through interstellar space. Galaxies are not merely star collections. They are ecosystems, dynamic, evolving, structured across multiple states of matter and energy. Some galaxies push size through activity rather than diameter. Quasars, powered by supermassive black holes consuming vast quantities of gas, can outshine entire galaxies. Jets launched from their poles extend hundreds of thousands of light-years into intergalactic space. Radio galaxies like Hercules exhibit twin jets stretching over 1.5 million light-years. These jets inflate radio lobes, enormous plasma bubbles that rival small galaxies in size. Energy output from such systems reshapes surrounding intergalactic gas, regulating star formation across cluster environments. So even single galactic cores can influence structures far beyond their stellar disks. But galaxies rarely exist in isolation. Gravity draws them into associations, pairs, triplets, groups, and eventually clusters containing hundreds or thousands of galaxies bound within shared gravitational wells. Before we reach those immense assemblies, one final perspective grounds galactic scale. If the Earth were a grain of sand, the solar system would be a small room. The Milky Way would span North America, and the distance to Andromeda would stretch across the Atlantic Ocean. Yet even that comparison collapses when we consider what lies beyond. Because galaxies themselves are only the beginning of large-scale cosmic structure. They are building blocks, nodes within networks far grander than individual stellar cities. As our journey continues outward, galaxies begin to gather. Their gravity intertwines, their motions synchronize within shared cosmic basins. We leave behind individual island universes and approach the vast archipelagos of galaxies known as clusters, where hundreds, sometimes thousands, of galaxies orbit together within structures millions of light-years wide, and where scale begins to eclipse even the imagination shaped by galaxies alone. Chapter 4. Galaxy Clusters. Cities become continents. As we move outward from individual galaxies, scale begins to shift in a way that challenges even astronomical intuition. A galaxy, vast as it is, does not drift alone through the universe. Gravity binds galaxies together just as it binds stars into galaxies. The result is the next rung in cosmic structure. Galaxy clusters. If galaxies are cities of stars, clusters are continents of galaxies. Enormous gravitationally bound systems containing hundreds to thousands of galaxies, immersed in vast halos of dark matter and permeated by oceans of superheated gas. To understand their scale, we begin close to home. The Milky Way resides within a modest gravitational association known as the local group. This is not yet a full cluster, but rather a small galaxy group containing more than 50 known galaxies. Its two dominant members are the Milky Way and Andromeda, each surrounded by smaller satellite galaxies such as the Triangulum galaxy and dozens of dwarf spheroidals. The local group spans roughly 10 million light-years. Even at this smaller scale, gravity governs the motion of every member. The Milky Way and Andromeda alone account for the majority of the group's mass, and their eventual merger will reshape the group's structure billions of years from now. But true galaxy clusters are far larger. They form at the intersections of cosmic filaments, where matter accumulates over billions of years. One of the nearest major examples is the Virgo cluster. Located about 54 million light-years from Earth, Virgo contains more than 1,500 galaxies, with some estimates exceeding 2,000 when faint dwarf members are included. Its diameter spans roughly 15 million light-years. At its center lies Messier 87, a supergiant elliptical galaxy containing trillions of stars and a supermassive black hole billions of times the Sun's mass. The black hole at M87's core was the first ever imaged directly by the Event Horizon telescope. Its shadow, silhouetted against glowing accretion gas, revealed a gravitational abyss larger than our solar system. But the galaxies themselves account for only a fraction of the cluster's mass. Between them lies the intracluster medium, an enormous reservoir of superheated gas reaching temperatures of tens of millions of degrees Kelvin. This gas emits powerful X-rays detectable by space telescopes such as Chandra and X-Newton. In fact, the hot gas within clusters outweighs all the stars in the galaxies combined. And beyond both lies the dominant mass component, dark matter. Clusters are embedded within colossal dark matter halos whose gravitational pull binds the entire structure together. Without dark matter, clusters could not exist as we observe them. Evidence for this invisible mass emerged dramatically in observations of gravitational lensing. When light from distant galaxies passes through a cluster, the cluster's gravity bends and magnifies that light, distorting background galaxies into arcs and rings. By mapping these distortions, astronomers can measure the cluster's total mass, revealing far more matter than visible stars and gas alone provide. One of the most famous examples demonstrating this effect is the Bullet cluster, a system formed by the collision of two galaxy clusters. As the clusters passed through one another, their hot gas components collided and slowed, visible in X-ray images. But gravitational lensing showed that most of the mass passed through unaffected, indicating that dark matter does not interact strongly with normal matter. This provided some of the clearest evidence for dark matter's existence. Cluster collisions are among the most energetic events since the Big Bang. Galaxies themselves rarely collide directly, as distances between stars are vast. But gravitational interactions distort galactic shapes, trigger starbursts, and feed central black holes. Shockwaves ripple through the intracluster gas, heating it further and generating radio emissions detectable across millions of light-years. Some clusters exhibit radio halos, diffuse emissions produced by relativistic electrons spiraling through magnetic fields. These halos can span the entire cluster, revealing the presence of large-scale magnetic structures. But not all clusters are the same. They vary in size, richness, and structure. Poor clusters may contain only a few hundred galaxies. Rich clusters can contain thousands. One of the most massive nearby clusters is the Coma cluster. Located about 320 million light-years away, it contains over 1,000 identified galaxies and spans more than 20 million light-years. At its core reside giant elliptical galaxies, surrounded by swarms of smaller companions. Coma's gravitational influence is immense. Its escape velocity exceeds several thousand kilometers per second. Gas trapped within its gravitational well remains heated to extreme temperatures, unable to cool and collapse into new stars. Thus, star formation within cluster cores is often suppressed. Clusters can regulate galactic evolution. Galaxies entering a cluster environment experience tidal forces, gas stripping, and gravitational harassment. Their spiral arms can be disrupted, their gas reservoirs removed by ram pressure stripping as they move through dense intracluster gas. Over time, Many spirals transform into ellipticals. Clusters are environments of both assembly and destruction, but some clusters push scale even further. Abell 1689, for instance, is one of the most massive clusters known, located over 2 billion light-years away. Its gravitational lensing effects are so strong that it magnifies extremely distant galaxies behind it, acting as a natural telescope into the early universe. Mass estimates place Abell 1689 at over a quadrillion times the mass of the Sun, 1 million billion solar masses bound together, and still, clusters themselves are not the largest structures. They gather, they align along filaments, they form superclusters. But before we ascend further, one more perspective anchors the scale of galaxy clusters. Imagine shrinking the Milky Way to the size of a coin. Within a cluster like Virgo, hundreds of such coins would float within a region the size of a large city. But the city would be filled not with air, but with gas heated to tens of millions of degrees. Invisible, X-ray luminous, threaded with dark matter scaffolding. Distances between coins would still measure tens of thousands of miles in this scale, yet gravity would bind them into a shared structure, orbiting a common center over billions of years. Clusters are not static. They evolve. They accrete new galaxies. They merge with other clusters. Their growth traces the expansion history of the universe itself. By studying clusters at different distances, astronomers peer backward in time, observing how structure formation unfolded across cosmic history. But the realization that awaited astronomers in the late 20th century reshaped everything. Clusters were not randomly distributed. They formed patterns, chains, walls, immense alignments stretching across hundreds of millions of light-years. Clusters, it turned out, were merely nodes within something even larger. Superclusters. Structures so vast they challenge the very definition of gravitational binding. And as our journey continues, scale once again expands beyond anything yet encountered. From millions of light-years to hundreds of millions. Chapter 5. Superclusters. The great gatherings of galaxies. As galaxy clusters assemble across millions of light-years, gravity continues its patient work. Clusters do not exist in isolation. They gather, they align. They form vast associations that stretch across incomprehensible distances. These structures are known as superclusters. If galaxies are cities and clusters are continents, then superclusters are the planetary landmasses of the cosmic landscape, the largest regions where gravity has drawn immense quantities of matter into coherent arrangements. But superclusters are different from clusters in one important way. Many are not fully gravitationally bound. The expansion of the universe competes with gravity at these scales. Some superclusters will eventually disperse as cosmic expansion accelerates, their member clusters drifting apart over tens of billions of years. Others, particularly their dense cores, may remain bound. So superclusters exist on the threshold between structure and dispersal, between gravity's pull and expansion's push. Our home resides within one, the Laniakea supercluster. Its name comes from the Hawaiian language, meaning immense heaven, a fitting title. Discovered through detailed mapping of galaxy motions in 2014, Laniakea redefined how astronomers understand our cosmic neighborhood. Previously, the Milky Way was thought to belong to the Virgo supercluster, but refined measurements of galactic velocity flows revealed a larger basin of gravitational attraction, encompassing Virgo and many surrounding clusters. Laniakea spans roughly 520 million light-years in diameter. It contains an estimated 100,000 galaxies. Its total mass is on the order of 100 quadrillion suns. To visualize this scale, imagine light leaving one edge of Laniakea at the dawn of multicellular life on Earth. That light would only now be reaching the opposite edge. Inside Laniakea, galaxies and clusters move along gravitational flow lines toward a central region known as the Great Attractor. This is not a single object, but a gravitational anomaly located near the Norma cluster. Obscured by dense dust in the plane of the Milky Way, it is difficult to observe directly, but its influence is measurable. Our galaxy, along with thousands of others, is moving toward it at hundreds of kilometers per second. It is a cosmic watershed. Just as rivers flow downhill toward ocean basins, galaxies flow along gravitational gradients toward supercluster centers. Mapping these flows revealed the true boundaries of Laniakea, a gravitational drainage basin in space. Yet Laniakea, vast as it is only one supercluster among many. Another colossal structure is the Shapley supercluster. Located about 650 million light-years away, Shapley is one of the most massive concentrations of galaxies in the nearby universe. It contains over 8,000 galaxies packed into a region roughly 650 million light-years across. Its mass is so immense that it significantly influences the motion of the local group, contributing to the gravitational pull we attribute partly to the Great Attractor. Clusters within Shapley are undergoing mergers, forming even larger structures over time. It is a dynamic environment where gravitational interactions shape galaxies at accelerated rates. But the largest known superclusters extend even further. The Hercules supercluster spans over 500 million light-years and contains multiple rich galaxy clusters connected by filaments of galaxies and gas. The Perseus-Pisces supercluster forms a chain-like structure stretching over 300 million light-years. These superclusters are not spherical. They are elongated, filamentary, thread-like. This reveals something profound about cosmic structure. Matter in the universe is not evenly distributed. It forms a cosmic web. Superclusters sit at the intersections of this web, nodes where filaments converge. Between them lie vast voids, regions nearly empty of galaxies. Some voids span hundreds of millions of light-years. If you lived inside one, the night sky would appear almost black, with few visible galaxies. The contrast between dense superclusters and empty voids gives the universe its large-scale texture. This structure emerged from tiny fluctuations in the early universe. After the Big Bang, matter was distributed nearly uniformly but not perfectly. Minute density variations, amplified by gravity over billions of years, grew into filaments, clusters, and superclusters. Computer simulations of cosmic evolution reproduce this web-like structure with remarkable accuracy. Dark matter plays the dominant role. It forms the scaffolding upon which visible matter accumulates. Without dark matter, superclusters would never have formed. Their gravitational wells would be too shallow to gather such vast quantities of galaxies. Inside superclusters, galaxy clusters orbit along filamentary highways of matter. Gas flows along these filaments. Galaxies migrate inward toward dense nodes. Over time, clusters merge, growing more massive. This hierarchical assembly continues even today, but superclusters also mark a limit. Beyond certain scales, gravity cannot overcome cosmic expansion. Structures larger than superclusters are not gravitationally bound in the traditional sense. They form patterns, alignments, and walls, but they do not behave as single gravitational systems. This distinction becomes critical as we move further outward, because the next structures we encounter challenge the very definition of what constitutes a single object. Before ascending to those extremes, one more perspective grounds the scale of superclusters. If the Milky Way were a grain of sand, a galaxy cluster would be a city. A supercluster would be a continent spanning oceans. Traveling at the speed of light, it would take hundreds of millions of years to cross. And yet, within this immensity, galaxies remain separated by vast distances. Even inside dense cluster cores, stars rarely approach one another. Space remains overwhelmingly empty. Superclusters are gatherings of islands across cosmic seas, but their scale shapes the motion of everything within them. Galactic trajectories bend toward supercluster centers. Cluster mergers release colossal energy. Shock waves ripple across tens of millions of light-years. Hot gas pools in gravitational basins. Dark matter halos overlap and merge. All of this unfolds over billions of years, too slow for direct human observation, yet measurable through redshift surveys and velocity mapping. The discovery of Laniakea illustrated how our understanding of structure continues to evolve. As mapping techniques improve, boundaries shift, new superclusters may be identified, existing ones redefined. The cosmic web grows clearer with each survey. Projects like the Sloan Digital Sky Survey and the Dark Energy Survey map millions of galaxies, revealing filaments and voids at ever greater resolution. These maps resemble neural networks, foam, sponges, patterns repeating across scales. They show that the universe is structured, not random, organized by gravity across unimaginable distances. But even superclusters are not the final step. They connect. They align into colossal filaments stretching billions of light years, walls of galaxies forming boundaries around titanic voids. Structures so vast they approach the scale of the observable universe itself. As we continue outward, we leave behind gravitationally bound systems and enter the domain of the largest known arrangements of matter, the cosmic web in its full expanse. Filaments, walls, and the first structures to exceed 1 billion light-years in size, where scale no longer feels astronomical, but universal. Chapter 6. Cosmic Filaments, the Highways of the Universe. Beyond superclusters, scale undergoes another transformation. Up to this point in our journey, every structure we have explored has been gravitationally bound in some meaningful way. Stars bound into galaxies, galaxies bound into clusters, clusters gathered into superclusters through shared gravitational basins. But as we move outward still further, gravity begins to lose its absolute grip. Expansion, the stretching of space-time itself, competes with attraction. Structures become less like singular objects and more like patterns, networks, threads. We enter the domain of cosmic filaments. If superclusters are continents, filaments are the tectonic ridges connecting them. Vast, elongated rivers of galaxies stretching across hundreds of millions to billions of light-years. They form the largest known coherent structures shaped by gravity's influence. When astronomers map the distribution of galaxies across the observable universe, they do not appear scattered randomly. They arrange themselves along filamentary structures, creating a web-like pattern known as the cosmic web. This web is the fundamental architecture of the universe on its largest scales. Galaxies, clusters, and superclusters all reside along these filaments, like beads strung on luminous threads. Between the filaments lie voids, immense regions nearly empty of galaxies. Together, filaments and voids form a structure that resembles foam, sponge, or neural tissue. The origin of filaments traces back to the earliest moments after the Big Bang. In the beginning, matter was distributed almost uniformly, but not perfectly. Tiny quantum fluctuations in density existed within the primordial plasma. As the universe expanded and cooled, dark matter began collapsing into denser regions under gravity. Because dark matter interacts weakly with radiation, it began structuring itself before ordinary matter could. These dark matter concentrations formed elongated sheets and filaments. Ordinary matter, gas, and eventually galaxies flowed into these gravitational channels. Over billions of years, the filamentary structure grew more pronounced. Simulations of cosmic evolution, such as the Millennium simulation, reproduce these patterns with remarkable accuracy. They show matter flowing along filaments into dense nodes, where clusters and superclusters form. Filaments are not merely chains of galaxies. They are immense reservoirs of dark matter and diffuse gas. In fact, most of the universe's ordinary matter is believed to reside not inside galaxies, but within the warm, hot, intergalactic medium threaded along filaments. This gas is difficult to detect. It is thin, faint, and heated to temperatures between 100,000 and 10 million Kelvin. Only through absorption lines in quasar light and faint X-ray emissions have astronomers begun mapping this hidden matter. One of the most studied filaments connects the galaxy clusters Abell 222 and Abell 223. X-ray observations revealed a bridge of hot gas stretching between them across tens of millions of light-years. This confirmed theoretical predictions that clusters grow by accreting matter along filaments. Galaxies move through these cosmic highways, guided by gravitational gradients. Over time, they drift inward toward dense cluster nodes. Filaments are the supply lines of structure formation. Without them, clusters would starve. But some filaments dwarf even these examples. The Sloan Great Wall, discovered in 2003 through the Sloan Digital Sky Survey, is one of the largest filamentary structures ever mapped. It stretches roughly 1.4 billion light-years across. To grasp this scale, consider that the Milky Way spans about 100,000 light-years. The Sloan Great Wall is 14,000 times wider. If the Milky Way were a coin, the Sloan Great Wall would span the width of a continent. It is not a solid wall. It is a dense alignment of galaxies, clusters, and filaments, forming a contiguous structure across space. Its discovery reshaped understanding of large-scale structure. Previously, astronomers believed cosmic homogeneity, the idea that matter is evenly distributed at the largest scales, would prevent structures larger than about 1 billion light-years from forming. Yet here was a structure exceeding that expectation. And it was not alone. Another colossal filamentary complex is the CFA2 Great Wall, discovered in the late 20th century. It spans roughly 500 million light-years. Though smaller than the Sloan Great Wall, it remains one of the first indications that galaxies form enormous sheet-like structures. Filaments often intersect at dense nodes. These intersections host the richest galaxy clusters. Matter flows along multiple directions into these gravitational basins, amplifying cluster growth. From a structural perspective, the universe resembles a three-dimensional spider web. Filaments are the strands, clusters are the junctions, voids are the empty spaces between. Computer simulations show that dark matter forms this scaffold first. Gas follows. Galaxies ignite along the densest ridges. This hierarchy of assembly is fundamental to modern cosmology. But filaments are not static. They evolve. They thicken as matter accretes. They stretch as cosmic expansion pulls on their endpoints. Some filaments will fragment. Others will merge. Over trillions of years, as expansion accelerates due to dark energy, many filaments will thin and disperse. Clusters bound at their nodes will remain gravitationally intact, but the filaments connecting them may dissolve. The cosmic web will slowly unravel, yet in the present epoch, filaments remain among the most dominant structures in existence. Observationally, mapping them is challenging. Galaxies serve as visible tracers, but most filament mass resides in dark matter and diffuse gas. Gravitational lensing offers one method of detection. By measuring how background galaxy light distorts as it passes through filament regions, astronomers infer the presence of mass even where little light exists. Radio observations also detect synchrotron emission from electrons accelerated along filament magnetic fields. These emissions hint that filaments possess large-scale magnetization, though its origin remains an area of active research. One hypothesis suggests that magnetic fields were seeded by early galaxies and amplified through structure formation. Another proposes primordial magnetic fields formed shortly after the Big Bang. Regardless of origin, these fields influence gas dynamics across vast scales. Filaments also act as thermal conduits. Gas falling into clusters along filament shocks and heats, contributing to intracluster medium growth. This process feeds cluster evolution. Thus, filaments are not merely structural. They are dynamic engines of matter transport. One of the most striking confirmations of filament structure comes from quasar absorption studies. As light from distant quasars travels toward Earth, it passes through intergalactic gas. Each encounter leaves spectral fingerprints, absorption lines revealing hydrogen and heavier elements. By mapping these absorption features across many sightlines, astronomers reconstruct filament distributions even where galaxies are sparse. These studies reveal that baryonic matter, ordinary matter, is far more widespread along filaments than previously thought. In fact, a significant fraction of the universe's missing baryons has been located within filament gas. The largest filaments approach lengths of billions of light years. They define the largest continuous structures shaped by gravity, but even they are not the absolute limit, because filaments sometimes align into even greater assemblies, walls, sheets, structures where multiple filaments converge into planar formations stretching across unimaginable distances. Before we reach those titanic constructs, one more perspective grounds filament scale. If the Milky Way were a grain of sand, a galaxy cluster would be a small town. A supercluster would be a continent. A filament like the Sloan Great Wall would span the circumference of a planet. And yet, even across such immensity, most of space remains empty. Galaxies line the filaments like lights on distant highways separated by enormous darkness. Traveling along one would mean crossing millions of light years between major galactic systems. But gravitationally, these highways define the flow of matter. Galaxies rarely wander far from them. They are born, migrate, and merge along these cosmic routes. The realization that the universe possesses this web-like architecture transformed cosmology. It revealed that structure formation is hierarchical, ordered, guided by dark matter's invisible hand. And as mapping surveys deepen, more filaments emerge. Longer, denser, more intricate. Yet even the largest filaments are only strands within a still greater design, because when multiple filaments align, they create walls of galaxies. Immense planar structures stretching across the observable universe. The next step outward takes us there, to the largest walls ever discovered. Structures so vast they test the limits of cosmological theory itself. Where size approaches the scale of the universe we can observe, and where the question of how large a structure can truly become begins to challenge the laws that shape them. Chapter 7. Cosmic Walls. The largest structures ever mapped. As we continue outward through the hierarchy of cosmic structure, the scale of existence expands once more. We have moved from stars to stellar nurseries, from nurseries to galaxies, from galaxies to clusters, from clusters to superclusters, from superclusters to filaments, the vast highways along which matter flows across the universe. Now those filaments begin to assemble into something even larger, planar structures of staggering scale, cosmic walls. If filaments are threads, walls are woven sheets. Immense alignments where multiple filaments intersect and flatten into vast, continuous planes of galaxies, clusters, and dark matter. They are among the largest known coherent structures in the observable universe. But unlike clusters, they are not gravitationally bound as single objects. Their scale exceeds the distance over which gravity can fully dominate cosmic expansion. Instead, they are shaped by the initial conditions of the early universe and the long evolution of matter flowing along the cosmic web. To understand cosmic walls, we begin with one of the earliest discoveries that hinted at their existence, the CFA2 Great Wall. Discovered in 1989 during the Center for Astrophysics Redshift Survey, it was one of the first indications that galaxies form structures far larger than clusters or superclusters alone. The CFA2 Great Wall stretches roughly 500 million light-years across. It is composed of dense concentrations of galaxies arranged in a contiguous sheet-like structure. When first mapped, it challenged prevailing assumptions about large-scale uniformity in the universe. Astronomers expected that beyond certain distances, matter would distribute relatively evenly. Yet the CFA2 Great Wall demonstrated that structure persisted on far larger scales than anticipated. But it was only the beginning. In 2003, using data from the Sloan Digital Sky Survey, astronomers identified an even larger structure. The Sloan Great Wall. This cosmic wall extends approximately 1.4 billion light-years in length. To grasp that scale, consider that light leaving one end of this structure before multicellular life arose on Earth would only now be reaching the other end. It contains numerous galaxy clusters, superclusters, and filament intersections forming a continuous planar arrangement. Its mass is incalculable in familiar terms, encompassing tens of thousands of galaxies and vast quantities of dark matter. Its discovery again pushed the limits of theoretical expectation. According to cosmological models based on inflation and large-scale homogeneity, structures beyond roughly 1 billion light-years should be exceedingly rare. Yet the Sloan Great Wall exists, and more have since been found. The Hercules Corona Borealis Great Wall, discovered through gamma-ray burst mapping, may be even larger. Estimated to span roughly 10 billion light-years, it challenges nearly every assumption about maximum structure size. However, its classification as a single coherent structure remains debated. Gamma-ray bursts trace star formation in distant galaxies, and clustering in their distribution suggests large-scale alignment. Whether this represents a true physical wall or statistical clustering remains an open question. Still, even conservative estimates place it among the largest structures ever identified. Another immense structure is the Boss Great Wall, discovered in 2016 through the Baryon Oscillation Spectroscopic Survey. It spans over 1 billion light-years and contains multiple superclusters connected through dense filaments. The Boss Great Wall includes 4 major superclusters, 2 large galaxy walls, and several filaments, forming a complex interconnected system. It is one of the most structurally intricate large-scale formations known. These walls reveal that matter in the universe is not only filamentary but also sheet-like. Computer simulations of cosmic evolution predicted this arrangement. Dark matter collapses along planes first, forming sheets, then along lines within those sheets, forming filaments, finally into nodes where filaments intersect, forming clusters. Thus, walls represent an intermediate structural scale between filaments and the broader cosmic web. They are regions where matter density remains higher across vast planar expanses. But walls are not solid. They are sparsely populated compared to galaxies themselves. Distances between galaxies within walls still measure millions of light-years. If one could travel across the Sloan Great Wall, the journey would involve immense stretches of darkness, punctuated by distant galactic clusters glowing like isolated archipelagos. Yet gravitational influence persists across the structure. Galaxies within walls exhibit correlated motion patterns. Their velocities trace the gravitational landscape sculpted by dark matter distribution. Mapping these motions helps astronomers reconstruct the mass structure underlying visible galaxies. One of the key methods used to identify walls is redshift surveying. By measuring how much a galaxy's light is stretched due to cosmic expansion, astronomers determine its distance. Plotting millions of galaxies in 3 dimensions reveals large-scale patterns. Walls appear as dense planar aggregations within these maps. Another method involves baryon acoustic oscillations. In the early universe, pressure waves rippled through hot plasma. When the universe cooled and atoms formed, these oscillations froze into matter distribution. Their imprint remains detectable in galaxy clustering patterns today. Studying these oscillations helps calibrate cosmic distances and confirms large-scale structure formation models that predict walls and filaments. But cosmic walls are not permanent. Over trillions of years, dark energy will continue accelerating cosmic expansion. Structures not gravitationally bound will drift apart. Walls will thin. Filaments will stretch. Eventually, only gravitationally bound clusters will remain intact. The cosmic web will fade into isolation. Yet in the current epoch, walls remain among the most imposing structures known. To place their scale in perspective, imagine shrinking the Milky Way to the size of a grain of sand. A galaxy cluster becomes a small hill. A supercluster becomes a continent. A cosmic wall like the Sloan Great Wall would stretch across an entire planet. Light itself requires over 1 billion years to cross it, but even these walls are not the final step in cosmic enormity. Because walls connect, they intersect. They form networks spanning the observable universe, the cosmic web in its full expression. A structure so vast it contains nearly all matter we can observe. At this scale, individual walls lose distinction. They become components of a still larger architecture, and beyond that lies the ultimate boundary of size we can meaningfully describe, the observable universe itself. But before reaching that horizon, one more structural scale awaits, the integrated cosmic web, the total network of filaments, walls, clusters, and voids forming the universe's grandest pattern. A structure not bound, not singular, yet unified in origin and evolution. As we move outward again, scale ceases to be measured in millions or billions of light years alone. It becomes measured in fractions of everything that exists within our observable reach, where the largest structures known approach the size of the universe itself. Chapter 8. The Integrated Cosmic Web, the universe's grand architecture. As our journey continues outward, individual structures begin to lose their separateness. Clusters blend into superclusters. Superclusters connect through filaments. Filaments merge into walls. Walls intersect across vast planes of matter. At this scale, the universe is no longer best understood as a collection of discrete objects. It becomes a single interconnected structure, the cosmic web. This is the largest known pattern of matter organization in existence, short of the observable universe itself. It is the scaffolding upon which all galaxies, clusters, and superclusters are built. Every luminous structure we have discussed so far exists as a node, strand, or intersection within this immense network. To visualize the cosmic web, astronomers rely on large-scale galaxy surveys and cosmological simulations. Projects such as the Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and the Dark Energy Survey have mapped the three-dimensional positions of millions of galaxies. When plotted in space, a striking pattern emerges. Galaxies are not distributed randomly. They trace enormous filaments intersecting at dense nodes, enclosing vast empty voids. The resulting structure resembles neural tissue, soap foam, or a sponge-like lattice. Simulations of cosmic evolution, such as the Millennium Simulation and Illustris, reproduce this web-like pattern with remarkable precision. These simulations begin shortly after the Big Bang, when the universe was nearly uniform but contained minor density fluctuations. Dark matter collapses first. Because it does not interact with radiation, it begins forming gravitational wells early in cosmic history. Ordinary matter falls into these wells, cooling and forming stars and galaxies. Over billions of years, gravity amplifies initial fluctuations. Filaments form where matter flows along gravitational gradients. Sheets form where filaments intersect. Clusters emerge at nodes where multiple filaments converge. This hierarchical growth produces the cosmic web. Its scale is staggering. Filaments can stretch for billions of light years. Walls extend across similar distances. Voids between them can measure hundreds of millions of light years in diameter. One of the largest known voids, the Boots void, spans roughly 330 million light years. Inside it, galaxies are exceedingly rare. If an observer lived within such a void, the night sky would appear almost empty, with few galaxies visible even through powerful telescopes. The contrast between dense filaments and empty voids defines the universe's large-scale structure. But the web is not static. Matter continues to flow along filaments toward dense nodes. Clusters grow, superclusters evolve, galaxies merge and transform. This dynamic flow resembles rivers feeding oceans. Gas, dark matter, and galaxies all migrate along gravitational currents. Observations confirm this movement. Galactic velocity surveys reveal coherent flows toward cluster centers. X-ray observations show gas streaming along filaments into clusters, heating as it falls into deep gravitational wells. Radio observations detect synchrotron emission from electrons accelerated within filament magnetic fields. The cosmic web is alive with motion. Most of the universe's baryonic matter resides not in galaxies, but within the warm, hot intergalactic medium spread along filaments. This gas, heated to between 100,000 and 10 million Kelvin, is diffuse and difficult to detect. Yet absorption studies of distant quasars reveal its presence. By analyzing spectral lines where quasar light passes through filament gas, astronomers map hidden reservoirs of matter. These findings resolved the long-standing missing baryon problem. Much of the ordinary matter predicted by cosmological models had not been observed in galaxies or clusters. It was located instead within the cosmic web itself. Dark matter dominates the web's mass. Gravitational lensing studies show that visible galaxies trace only a fraction of total matter distribution. Light from distant galaxies bends as it passes through filament regions, revealing invisible mass concentrations. This confirms that dark matter forms the web's underlying framework. Galaxies illuminate the structure. Dark matter shapes it. Magnetic fields thread through the web as well. Their origin remains debated. Some theories suggest they formed during early cosmic phase transitions. Others propose they were seeded by early star formation and amplified through turbulence. Regardless, they influence gas dynamics, cosmic ray propagation, and galaxy formation processes across vast scales. The cosmic web also regulates star formation. Galaxies embedded within dense filaments tend to have higher gas accretion rates. This fuels star formation and black hole growth. Conversely, galaxies within voids often evolve more slowly, with fewer interactions and reduced gas inflow. Environment shapes galactic destiny. Clusters at filament intersections represent the densest evolutionary hubs. Here, mergers are frequent. Galactic morphologies transform rapidly. Elliptical galaxies dominate cluster cores, while spirals persist in filament outskirts. This gradient reflects the intensity of gravitational interaction. Mapping the cosmic web requires vast observational campaigns. Spectroscopic surveys measure redshift to determine galaxy distances. Weak, gravitational lensing maps dark matter distribution. X-ray telescopes detect hot gas in clusters and filaments. Radio arrays trace magnetic fields and relativistic particles. Combining these observations produces three-dimensional reconstructions of the web. One of the most detailed maps to date comes from the Sloan Digital Sky Survey, charting the positions of over 1 million galaxies. These maps reveal filaments stretching across billions of light years, walls connecting clusters, and voids expanding between them. But even these surveys sample only a fraction of the observable universe. Beyond mapped regions, the web continues. Its full extent approaches the boundary of what light has had time to reveal since the Big Bang. Computer simulations extend beyond observational limits. They model cosmic structure formation from early density fluctuations to present-day web complexity. These simulations show that the web will continue evolving. Clusters will merge into larger systems. Filaments will thin as dark energy accelerates expansion. Eventually, gravitationally unbound structures will drift beyond each other's cosmic horizons. The web will fragment. In trillions of years, observers within surviving clusters may see only their local gravitational group. All other galaxies will have receded beyond observable reach. But in the present epoch, the cosmic web remains intact. A vast interconnected lattice spanning the observable universe. To grasp its scale, imagine shrinking the Milky Way to the size of a grain of sand. A galaxy cluster becomes a hill. A supercluster becomes a continent. A filament becomes a planetary ridge. The integrated cosmic web would span a world larger than imagination, its strands encircling everything within view. Light crossing the web from one extreme to another would require billions of years. Yet even this immense structure is not the final boundary, because the cosmic web exists within something larger still, the observable universe, the full sphere of space from which light has had time to reach us since the beginning of cosmic expansion. It contains every filament, every wall, every cluster, every galaxy we can detect. Beyond it lies more universe, but forever beyond observational reach. As we continue outward, we approach that ultimate horizon. where size ceases to refer to structures within the universe, and instead refers to the universe itself. Chapter 9. The Observable Universe. The largest thing we can ever see. As we move beyond filaments, beyond walls, beyond even the integrated cosmic web, we arrive at the greatest boundary accessible to observation. Not the edge of existence, not the edge of all reality, but the edge of what light has had time to reveal, the observable universe. It is the largest scientifically measurable structure we can meaningfully describe. Everything we have explored so far exists within it. Every galaxy, every cluster, every filament and void, every star that has ever burned, all of it resides inside this vast cosmic horizon. To understand why this boundary exists, we must return to the beginning. Approximately 13.8 billion years ago, the universe emerged from an extremely hot, dense state. The event we call the Big Bang was not an explosion into space, but an expansion of space itself. From the first fraction of a second, space-time began stretching. Matter and radiation expanded with it. As the universe grew, light began traveling outward in all directions. But light travels at a finite speed, approximately 299,792 kilometers per second. This speed limit defines our observable boundary. We can only see as far as light has had time to travel since the universe became transparent, yet here is where scale becomes counterintuitive. If the universe is 13.8 billion years old, one might expect the observable radius to be 13.8 billion light-years, but expansion changes the calculation. As light traveled toward us, the space it crossed continued expanding. Galaxies that emitted that light are now much farther away than the distance light traveled. Accounting for expansion, the observable universe has a present-day radius of roughly 46.5 billion light-years. Its diameter is about 93 billion light-years. That is the size of the cosmic sphere we can observe from Earth. Within it reside an estimated 2 trillion galaxies, according to deep field surveys conducted by the Hubble Space Telescope and extrapolated through statistical modeling. Each galaxy contains billions to trillions of stars. The total number of stars in the observable universe likely exceeds 1,022, a number so large it defies linguistic expression. More stars than grains of sand on all Earth's beaches combined. But galaxies themselves account for only part of the universe's content. The observable universe also contains vast reservoirs of intergalactic gas, dark matter halos, radiation fields, neutrinos, and dark energy. In terms of energy density, ordinary matter, the atoms forming stars, planets, and people, comprises only about 5% of the total cosmic inventory. Dark matter accounts for roughly 27%. Dark energy, the driver of accelerated expansion, constitutes about 68%. Thus, most of the observable universe is invisible, its structure shaped by forces we detect indirectly. Mapping the observable universe requires large-scale surveys spanning decades. Projects such as the Sloan Digital Sky Survey, the Dark Energy Survey, and the 2-micron All-Sky Survey have charted millions of galaxies. Cosmic microwave background observations from satellites like COBE, WMAP, and Planck reveal the earliest observable light. This radiation originated about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen. Before this epoch, the universe was opaque plasma. Light could not travel freely. The cosmic microwave background represents the oldest light we can detect. It forms a spherical shell around us, marking the farthest electromagnetic signal accessible to observation. Beyond it lies the cosmic dark age, earlier epochs detectable only through indirect signatures such as gravitational waves or neutrino backgrounds. The observable universe is isotropic on large scales. In every direction, when averaged across hundreds of millions of light-years, matter distribution appears statistically uniform. This supports the cosmological principle, the assumption that the universe is homogeneous and isotropic at the largest scales, yet local structures, filaments, walls, and voids create complex patterns within that broader uniformity. Observationally, deep field imaging offers glimpses into this vast structure. The Hubble ultra-deep field, for example, captured a tiny patch of sky roughly the size of a grain of sand held at arm's length. Within that speck, thousands of galaxies appear, each containing billions of stars. Extrapolated across the entire sky, the number of galaxies becomes astronomical in the truest sense. The James Webb Space Telescope has extended this reach further, observing galaxies formed less than a few 100 million years after the Big Bang. These early galaxies appear smaller, more irregular, yet already numerous. They trace the early formation of the cosmic web. Looking deeper into space is equivalent to looking back in time. Because light takes time to travel, observing distant galaxies reveals earlier cosmic epochs. The observable universe is therefore also a time capsule. At its outermost regions, we see the universe as it existed billions of years ago. Closer regions reveal more recent history. This layered time structure allows astronomers to reconstruct cosmic evolution, but the observable universe has a limit not only in distance, but in causal connection. Some galaxies we observe emitted their light when they were closer to us. Due to accelerated expansion, they are now receding faster than light relative to our position. Their current light will never reach us. We see them as they were, but never as they are now. Over time, more galaxies will cross this cosmic event horizon. Future observers will see a shrinking universe. Clusters beyond our local gravitational group will fade from view. In trillions of years, only the remnants of our merged local group may remain visible. All other galaxies will lie beyond observational reach. But in the present cosmic era, we inhabit a uniquely privileged epoch. Expansion has not yet erased the visibility of large-scale structure. We can observe the cosmic web, map superclusters, detect the microwave background, and measure the universe's geometry. To place the observable universe's scale into perspective requires abandoning ordinary analogy. If the Milky Way were a grain of sand, the observable universe would be a sphere thousands of kilometers wide, containing trillions of such grains suspended in darkness. Light would require tens of billions of years to cross it. Yet even this immense sphere is not the entire universe. It is only the portion from which light has reached us. Beyond its boundary, more galaxies likely exist, more filaments, more walls, possibly infinite structure, but forever unobservable. The observable universe is therefore both vast and limited, immense beyond comprehension, yet bounded by the finite speed of light in the age of cosmic expansion. It is the largest structure we can measure, the largest thing we can ever see. And still, our journey is not complete. Because even within the observable universe exist structures so enormous they span significant fractions of it. Structures that test the limits of cosmological theory, some confirmed, some debated, all pushing the definition of size to its extreme. As we continue outward, we leave behind the universe as a whole and examine the largest individual structures contained within it. Objects so vast they stretch across billions of light-years, where scale approaches the horizon of everything observable, and where the definition of a single structure begins to blur into the universe itself. Chapter 10. The Hercules Corona Borealis Great Wall, the largest structure ever proposed. As we continue outward through the hierarchy of cosmic scale, we arrive at a structure so vast that it challenges the limits of modern cosmology. A structure so immense that if confirmed in full physical coherence, it would be among the largest known arrangements of matter ever identified. The Hercules Corona Borealis Great Wall. Its name reflects the region of sky in which it appears, spanning the constellations Hercules and Corona Borealis. But its physical scale extends far beyond those familiar star patterns. Estimated to stretch roughly 10 billion light-years across, this proposed structure approaches 1/9 the diameter of the observable universe itself. To grasp the magnitude of such a claim requires careful scientific grounding. Unlike galaxy clusters, superclusters, or filamentary walls mapped directly through galaxy surveys, the Hercules Corona Borealis Great Wall was identified using gamma-ray bursts as traces. Gamma-ray bursts, or GRBs, are among the most energetic events in the universe. They occur when massive stars collapse into black holes or when neutron stars merge. These events release intense beams of gamma radiation detectable across billions of light-years. Because GRBs originate in star-forming galaxies, their spatial distribution reflects underlying matter distribution at cosmological scales. Astronomers analyzing GRB data noticed a statistically significant clustering of bursts within a particular region of the sky. When plotted in three-dimensional space using redshift distances, these bursts appeared aligned along an enormous arc-like structure. This alignment suggested the presence of an underlying large-scale matter concentration. Thus, the Hercules Corona Borealis Great Wall was proposed. Its estimated length of 10 billion light-years far exceeds previously known structures like the Sloan Great Wall or the Boss Great Wall. If treated as a contiguous structure, it would violate expectations derived from the cosmological principle. The cosmological principle states that at sufficiently large scales, the universe should appear homogeneous and isotropic. Structures larger than roughly 1 to 2 billion light-years should be statistically improbable, yet the Hercules Corona Borealis Great Wall appears far larger. This has led to ongoing debate. Some researchers argue that the GRB clustering represents statistical anomaly rather than true structural coherence. Gamma-ray bursts are rare, and detection is influenced by observational bias. Instrument sensitivity, sky coverage, and detection thresholds can shape apparent distributions. Others suggest that the structure may represent a combination of multiple adjacent filaments and walls rather than a single unified entity. In this interpretation, the apparent continuity arises from projection effects or sampling limitations. However, even conservative interpretations acknowledge that the region contains an unusually high density of GRB-producing galaxies. Whether a single wall or a network of interconnected filaments, its scale remains extraordinary. To understand what a 10 billion light-year structure implies, consider the following perspective. Light leaving one end of the structure before the formation of Earth would only now be reaching the opposite side. Its span encompasses a significant fraction of cosmic history. Within it would reside tens of thousands of galaxy clusters, millions of galaxies, and untold quantities of dark matter and intergalactic gas. But physical binding at such scales is impossible. Gravity cannot hold together a structure spanning billions of light-years against cosmic expansion. Instead, such a structure represents a pattern of matter density rather than a single gravitational system, a region where initial density fluctuations in the early universe were slightly amplified. Over billions of years, those fluctuations guided matter into elongated alignments. This interpretation aligns with large-scale structure simulations. The early universe contained density variations seeded by quantum fluctuations during cosmic inflation. These variations, though minute, determined where matter would accumulate over time. Regions slightly denser than average attracted more matter. Filaments formed along gravitational gradients. Walls formed where filaments intersected. The largest alignments represent the amplified outcomes of these primordial fluctuations. Thus, the Hercules Corona Borealis region may represent an extreme but natural extension of cosmic web formation. Its discovery highlights both the power and the limitations of observational cosmology. Gamma-ray bursts allow us to probe vast distances beyond typical galaxy surveys, but their rarity introduces statistical uncertainty. As more GRBs are detected through missions like NASA's Swift Observatory and future high-energy telescopes, the structure's coherence may become clearer. If confirmed in full, it would demand refinements to cosmological models, not necessarily overturning the cosmological principle, but constraining the statistical limits of large-scale structure formation. Some theoretical work suggests that inflationary fluctuations could produce rare, exceptionally large alignments without violating overall homogeneity. In this view, the Hercules Corona Borealis Great Wall would be an extreme outlier rather than a contradiction. Regardless of classification, its proposed scale forces reconsideration of what constitutes a structure. At billions of light-years, individual gravitational interaction between components becomes negligible. Clusters within the alignment evolve independently. Galaxies within clusters follow local gravitational dynamics. The wall itself is defined by spatial correlation rather than dynamical unity. This raises philosophical questions about cosmic structure definition. At what scale does pattern become object? When does statistical alignment qualify as structural identity? Astronomers grapple with these questions as surveys reveal ever larger formations. Yet even if the Hercules Corona Borealis Great Wall represents multiple adjacent structures rather than a single continuous wall, its region remains among the most massive large-scale alignments known. Its discovery underscores how much of cosmic structure remains to be mapped. Only a fraction of the observable universe has been surveyed at high resolution. Future missions, including next-generation spectroscopic surveys and deep-field observatories, will refine three-dimensional maps of galaxy distribution. These efforts may confirm, subdivide, or even surpass the Hercules Corona Borealis structure. Already, other immense formations rival its scale in complexity, if not in singular length. The huge large quasar group, for example, spans roughly 4 billion light-years. Quasars within it appear aligned across vast distances, again raising questions about maximum structure size. Such discoveries reveal that the universe retains structural coherence at scales once thought impossible. But even the Hercules Corona Borealis Great Wall, immense as it is, remains contained within the observable universe. It occupies a fraction of cosmic volume. Beyond it lie other filaments, other walls, other voids stretching toward the observable horizon. To ground its scale one final time, imagine shrinking the Milky Way to the size of a grain of sand. A galaxy cluster becomes a pebble. A supercluster becomes a continent. The Sloan Great Wall becomes a planetary circumference. The Hercules Corona Borealis Great Wall would span multiple planets in this analogy. A structure so vast it defies any terrestrial comparison. Yet it exists not as a solid wall, but as a faint statistical alignment of galaxies across incomprehensible distance, the largest pattern ever proposed. And still, our journey outward continues, because beyond specific named structures lies an even greater question. What is the largest coherent structure that can physically exist? What limits structure formation? What defines the maximum scale of gravitational influence? To answer that, we move next into the physics governing size itself, the scale at which cosmic expansion overtakes gravity, where structure formation ends, and where the universe transitions from organized architecture into ultimate largeness without boundary. Chapter 11, The Scale Limit of Structure, where gravity yields to expansion. As we move beyond named walls and filaments, beyond even the largest proposed alignments of galaxies, we reach a boundary defined not by observation alone, but by physics. Up to this point in our journey, every structure has emerged through the same fundamental process: gravity pulling matter together over time, from stars to galaxies, from galaxies to clusters, from clusters to superclusters, and onward into filaments and walls. Structure formation follows a hierarchical pattern governed by gravitational attraction acting on primordial density fluctuations. But gravity does not operate alone. it competes with another force embedded within spacetime itself: cosmic expansion. To understand the largest possible structures, we must understand how these two influences interact. The universe has been expanding since its earliest moments. Not galaxies moving through space, but space itself stretching. Distances between gravitationally unbound objects increase over time. For billions of years after the Big Bang, gravity and expansion existed in tension. Matter slowed expansion. Dense regions collapsed into structure. Clusters and filaments formed as gravity sculpted the cosmic web. But approximately 5 billion years ago, expansion began accelerating. Observations of distant type Ia supernovae revealed that galaxies were receding faster than expected. This acceleration is attributed to dark energy, a pervasive energy component embedded within spacetime. Dark energy exerts negative pressure. It drives expansion rather than resisting it. Its effects become dominant at large scales where matter density is low. Thus, structure formation encounters a fundamental limit. There exists a maximum scale beyond which gravity cannot overcome expansion to form coherent structures. This scale is sometimes referred to as the homogeneity scale, or the maximum turnaround radius for bound systems. Current cosmological models place this limit at roughly 1 billion light-years. Structures significantly larger than this cannot be gravitationally bound as single systems. They may appear aligned or connected, but their components do not share a common gravitational future. Instead, expansion will gradually separate them. This explains why galaxy clusters remain bound while superclusters often do not. Within clusters, gravitational attraction dominates local expansion. Galaxies orbit cluster centers. Gas remains confined within gravitational wells. But superclusters, spanning hundreds of millions of light-years, exist at the threshold. Some regions remain bound, others drift apart. Filaments and walls extending billions of light-years are not bound structures at all. They are density patterns shaped by initial conditions rather than gravitational unity. To visualize this, imagine ripples forming on a stretching rubber sheet. Local depressions deepen where gravity pulls matter inward, but the sheet itself continues stretching. If depressions lie too far apart, they cannot merge into a single basin. They remain separate despite surface alignment. Dark matter plays a critical role in determining structure scale. Because it dominates mass content, its distribution sets the gravitational landscape. Simulations show that dark matter halos merge hierarchically up to cluster scales. But beyond that, expansion dilutes density, contrasts too quickly for gravitational collapse to proceed. Thus, clusters represent the largest gravitationally virialized structures. Superclusters represent transitional systems. Filaments and walls represent large-scale correlations rather than bound entities. This scale limit also defines the largest structures that will remain observable over cosmic time. As expansion accelerates, distant galaxies will recede beyond our event horizon. Light emitted in the future from those galaxies will never reach us. Clusters not gravitationally bound to our local group will fade from view. In trillions of years, observers within our merged galactic remnant may see only a handful of nearby galaxies. The cosmic web will appear to dissolve. This future isolation underscores how structure scale interacts with cosmic expansion. The largest structures we see today are products of a universe where gravity had sufficient time to shape matter before dark energy dominance. Had dark energy been stronger earlier, large-scale structure might never have formed. Galaxies themselves could have remained rare, clusters non-existent. Conversely, if dark energy were absent, gravity might have eventually reversed expansion entirely. The universe could have collapsed in a big crunch, compressing all structure back into dense singularity. The balance between gravity and expansion defines the architecture of the cosmos. Modern cosmology uses large-scale structure to constrain dark energy properties. By measuring cluster distribution, filament alignment, and void expansion, astronomers infer how cosmic acceleration evolves. Surveys such as Euclid, the Vera Rubin Observatory's legacy survey of space and time, and the dark energy spectroscopic instrument aim to refine these measurements. Their maps will chart tens of millions of galaxies, revealing structure at unprecedented resolution. These observations test whether dark energy behaves as a cosmological constant or evolves over time. They also constrain alternative theories such as modified gravity. But beyond observational cosmology, the scale limit of structure has theoretical implications. Inflationary cosmology predicts that density fluctuations follow a specific statistical distribution. Structures larger than certain scales become exponentially unlikely. Thus, discoveries like the Hercules Corona Borealis alignment spark debate. Do they represent true physical anomalies, or statistical extremes within expected variance? The answer depends on improved mapping and modeling. Another factor influencing structure scale is baryon acoustic oscillations. In the early universe, pressure waves propagated through hot plasma. When atoms formed, these oscillations froze into matter distribution. They established a characteristic clustering scale of about 500 million light-years. This scale appears repeatedly in galaxy correlation measurements. It serves as a cosmic standard ruler for distance measurement. It also limits the coherence of larger structures. Beyond certain scales, density fluctuations diminish. Matter distribution approaches statistical uniformity. Thus, walls spanning billions of light-years represent alignments of multiple correlated regions, rather than single collapse structures. One of the most profound consequences of the structure scale limit is the eventual fate of cosmic architecture. As dark energy accelerates expansion, filamentary bridges between clusters will thin. Gas flows will cease. Cluster mergers will decline. Galaxies outside gravitationally bound groups will drift away irreversibly. Over hundreds of billions of years, the visible universe from any single vantage point will shrink dramatically. Only local gravitational islands will remain observable. The cosmic web will persist physically, but observationally fragment, each bound cluster becoming an isolated universe unto itself. This future isolation reveals that the largest observable structures exist only during a limited cosmological epoch. We live during the era when cosmic structure is most visible. Early in cosmic history, structure had not yet formed. Late in cosmic history, expansion will obscure it. Thus, the present epoch offers a uniquely comprehensive view. But the scale limit of structure also informs our understanding of the universe's geometry. Large-scale surveys confirm that matter distribution becomes homogeneous beyond several hundred million light-years. This supports the assumption that the universe is flat on large scales. Spatial curvature measurements from the cosmic microwave background further reinforce this conclusion. Flat geometry allows infinite spatial extent, though observationally we remain limited to the observable sphere. Thus, the largest structures that can physically form are constrained not only by gravity and expansion, but by initial density conditions and cosmic geometry. To ground this scale once more in perspective, imagine shrinking the Milky Way to the size of a grain of sand. A galaxy cluster becomes a hill. A supercluster becomes a continent. Filaments become planetary ridges. Walls become global tectonic plates. The scale limit of structure would represent the maximum size any such plate could form before planetary curvature and expansion tore it apart. Beyond that, alignment replaces cohesion. Pattern replaces object. This boundary marks the transition between structure and distribution, between architecture and background. Yet our journey outward continues still. Because even if gravity cannot bind larger structures, the universe itself remains larger than any structure within it. Beyond scale limits lies totality, the full expanse of cosmic existence, not just the observable portion, but the entire universe beyond our horizon, possibly infinite, possibly finite but unbounded. In the next step, we move beyond structure entirely, into the geometry, size, and extent of the universe as a whole, where the concept of largest thing transforms again. From the largest structure within the universe to the universe itself as the largest entity that exists. Chapter 12. The entire universe beyond observation, the largest possible physical expanse. As we move beyond the scale limit of structure, beyond the reach of gravitational cohesion, beyond the cosmic web and its largest alignments, we arrive at a boundary defined not by matter, but by perception. The boundary of the observable universe is not the boundary of the universe itself. It is only the limit imposed by light's travel time. Beyond it, the universe continues. How far it extends remains one of the most profound unanswered questions in cosmology. This chapter explores the largest thing that can physically exist within current scientific understanding, the universe in its totality, not merely the observable portion, but the full cosmic expanse beyond observational reach. To approach this scale, we must first understand what the observable universe truly represents. The observable universe is a sphere centered on the observer. Its radius, roughly 46.5 billion light-years, marks the farthest distance from which light has had time to reach us since the universe became transparent. But this sphere is not unique to Earth. An observer in a galaxy billions of light-years away would also see a 46.5 billion light-year radius observable universe centered on their own position. Thus, observable universes overlap like bubbles. Each observer perceives themselves at the center. This does not imply special location. It reflects the finite speed of light and uniform cosmic expansion. The full universe must therefore extend far beyond any single observable sphere. But how much farther? Observations of the cosmic microwave background provide the strongest constraints. Measurements of temperature fluctuations across the sky reveal the universe's geometry. Current data indicate that space is flat within a margin of error less than 0.4%. Flat geometry implies that the universe may be infinite in spatial extent. If space is truly flat and unbounded, then it has no edge, no boundary, no outer wall. It simply continues indefinitely in all directions. An infinite universe would contain infinite galaxies, infinite stars, infinite cosmic structures repeating across immeasurable distance. But infinite extent is not the only possibility. The universe could be finite yet unbounded, analogous to the surface of a sphere in higher dimensions. Travel far enough in one direction, and one might theoretically return to the starting point, though cosmic expansion complicates such traversal. Observationally detecting such curvature would require measuring deviations in cosmic microwave background patterns across the entire sky. Thus far, no such curvature has been detected within measurable limits. If the universe is finite, its minimum size must be at least several hundred times larger than the observable universe. Some estimates suggest a lower bound of 23 trillion light-years in diameter, but the true size could be vastly larger still. Even trillions of light-years might represent only a small fraction of total cosmic extent. Inflationary cosmology offers additional insight. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion known as cosmic inflation. During inflation, space-time expanded faster than light, smoothing out density irregularities and driving the universe toward flatness. Inflation predicts that the observable universe represents only a tiny patch of a vastly larger inflating space. Some inflationary models suggest that the universe may be at least 1,023 times larger than the observable portion. Others allow for effectively infinite expansion. Thus, the largest physical structure may not be any cluster, wall, or filament. It may be the total universe itself, an expanse so vast that even light traveling for trillions of years could never cross it. To ground this scale, imagine shrinking the observable universe to the size of Earth. If inflationary estimates hold, the full universe could be larger than the solar system, the galaxy, or even beyond analogy. Comparison fails because all familiar structures exist within the universe, not outside it. The universe defines the frame of comparison itself. Yet despite its enormity, the universe remains governed by measurable physical laws. Its expansion rate is quantified through the Hubble constant, its composition measured through cosmic background radiation and large-scale structure surveys, its age estimated through stellar evolution and nucleosynthesis modeling. The observable universe contains roughly 2 trillion galaxies, but beyond it may lie trillions upon trillions more. Galaxies whose light has not yet reached us, galaxies that may never be observable due to accelerating expansion. The cosmic event horizon defines this ultimate observational limit. Beyond a certain distance, expansion carries galaxies away faster than light relative to us. Their emitted photons can never overcome expanding spacetime to reach Earth. Thus, parts of the universe remain permanently unobservable. Even if humanity survives for trillions of years, those regions will remain beyond detection. In this sense, the largest thing in existence is not only vast but partially unknowable. Its full structure lies beyond empirical verification, yet cosmological models allow inference. If inflation occurred as predicted, then space beyond the observable universe likely contains the same large-scale structure we see locally: filaments, voids, clusters, walls repeating across immense expanses, or perhaps entirely different configurations depending on inflationary field fluctuations. Some theories even propose that distant regions of the universe may exhibit different physical constants, though such ideas remain speculative. Still, within standard cosmology, the universe beyond observation remains structurally similar. An extension of the cosmic web without boundary within measurable reach. The concept of the entire universe as the largest structure introduces philosophical implications as well. Everything that exists physically resides within it. Every particle, every field, every galaxy, it contains all measurable energy and space-time geometry. There is no external vantage point from which to observe it wholly. It is both the container and the contained, the stage and the actors. Even time itself is embedded within the universe's evolution. Thus, measuring its total size requires indirect inference rather than direct observation. Future observations may refine lower bounds on cosmic size. More precise cosmic microwave background measurements could detect subtle curvature. Gravitational wave background studies might reveal inflationary signatures constraining expansion magnitude. But a definitive measurement of total cosmic extent may remain forever beyond reach. The universe may be infinite, or finite yet incomprehensibly vast. Either possibility places it as the largest physical entity conceivable within known physics. Yet even here, our journey outward does not entirely end, because modern cosmology entertains possibilities beyond a single universe. Theories arising from inflation, quantum mechanics, and string theory suggest that our universe may be one region within a far greater structure. A multiverse. If such frameworks hold, then even the total universe we inhabit may not be the largest thing in existence. Instead, it may be one bubble within a cosmic foam of universes. Each with its own space-time, constants, and physical laws, the scale of existence would expand again, from universe to multiverse. And as we continue outward, the concept of largest thing transforms once more, from physical structure to the totality of all cosmic domains that may exist. Chapter 13. Inflationary Bubbles. Universes beyond our own. As we move beyond the totality of our own universe, beyond even the question of whether space is finite or infinite within its own domain, modern cosmology introduces a possibility that expands scale once again. A possibility rooted in physics, not fantasy. The inflationary multiverse. To understand this, we must return to the earliest known epoch of cosmic history, the era of cosmic inflation. Inflation is a theoretical framework developed to explain several observed properties of the universe. Among them are the large-scale uniformity of cosmic microwave background radiation, the flatness of space-time geometry, and the absence of magnetic monopoles predicted by certain particle theories. According to inflationary theory, the universe underwent an extremely rapid expansion within the first fraction of a second after the Big Bang. During this phase, space-time expanded exponentially. Distances doubled again and again in intervals far shorter than a second. Regions once microscopically small were stretched to astronomical scales. Quantum fluctuations embedded within this inflating space-time were magnified, becoming the seeds of future cosmic structure. These fluctuations would later evolve into galaxies, clusters, and the cosmic web. But inflation may not have occurred everywhere at once, nor ended everywhere simultaneously. Many inflationary models predict that inflation is eternal. In this framework, inflation continues in some regions of space-time even as it ends in others. Where inflation ends, a universe like ours forms. Where it continues, space-time keeps expanding exponentially. The result is a vast inflating background within which localized regions stop inflating and become individual universes. These regions are often called bubble universes. Each bubble is causally disconnected from the others. Light cannot travel between them because inflationary expansion separates them faster than signals can propagate. Thus, each bubble becomes its own observable universe, its own space-time domain, its own cosmic history. Our universe may be one such bubble. If inflation is eternal, then bubbles form continuously, an unending cosmic foam of universes, each nucleating within the inflating substrate. The scale of this structure dwarfs even the concept of an infinite single universe, because each bubble may contain infinite space within itself, and there may be infinitely many bubbles. Inflationary bubbles arise through quantum tunneling processes within the inflation field. The inflation field, sometimes modeled as a scalar field, possesses energy states analogous to valleys within a potential landscape. When a region tunnels from a higher energy inflationary state to a lower one, inflation ends locally. That region reheats, particles form, and a hot Big Bang phase begins. Inside the bubble, expansion continues, but at a far slower rate than inflationary expansion outside it. From within, it appears as though a universe has begun, but outside, inflation still rages, separating bubbles at superluminal effective speeds. One of the most profound consequences of this framework is that different bubbles may possess different physical constants. The vacuum energy, particle masses, force strengths, and symmetry breakings could vary depending on how inflation ended in each region. This idea connects to string theory landscapes, where vast numbers of possible vacuum states exist. Each bubble universe might realize a different set of physical laws. Some universes might expand too rapidly for galaxies to form. Others might collapse quickly. Some might contain entirely different particle families. Only a small subset might support complex chemistry and life. This selection framework is sometimes invoked in anthropic reasoning. We observe a universe compatible with life because only such universes can host observers. Observationally, detecting other inflationary bubbles is extremely challenging. Direct signals cannot cross inflationary space. However, some models predict that bubble collisions could leave imprints on the cosmic microwave background. These would appear as circular temperature anomalies. Searches for such signatures have been conducted using Planck and WMAP data. Thus far, no conclusive evidence of bubble collisions has been found, but observational limits remain incomplete. Future cosmic microwave background polarization studies may refine detection sensitivity. Gravitational wave backgrounds from inflationary processes may also provide indirect evidence of eternal inflation. If detected, they could support the existence of multiple inflationary regions. The scale of the inflationary multiverse, if real, defies all conventional measurement. Because inflation continues expanding space-time between bubbles, the distance separating universes increases faster than light. Thus, even if two bubbles formed near one another initially, they would rapidly become causally disconnected. No physical travel or communication could occur between them. Each universe becomes its own isolated cosmic domain. Within each bubble, cosmic structure forms hierarchically, just as in our own. Galaxies, clusters, filaments, and webs arise from amplified density fluctuations. From inside, each bubble appears as a complete universe, but from the broader inflationary perspective, they are merely localized regions where inflation has ceased, like air bubbles forming within boiling liquid. The inflating background represents the largest physical structure predicted by inflationary cosmology. An ever-expanding substrate spawning universes endlessly. Its size cannot be measured, because inflation never fully ends. Its volume increases exponentially. New bubbles form continuously. Old ones drift ever farther apart. This structure is sometimes referred to as Level 2 in multiverse classification frameworks, distinct from Level I, which refers to regions beyond our observable universe within the same spacetime. Level 2 encompasses separate post-inflationary universes with potentially different physical constants. Theoretical support for inflationary multiverses arises from quantum field theory and general relativity, but empirical verification remains limited. Inflation itself is strongly supported by observational data. The multiverse extension remains plausible but unconfirmed. Nevertheless, its implications for cosmic scale are profound. If eternal inflation is correct, then our universe is not the largest thing that exists. It is one bubble within a far greater inflating continuum. To ground this scale, imagine shrinking our observable universe to the size of a grain of sand. An inflationary multiverse might resemble an ocean filled with such grains forming endlessly, each grain containing trillions of galaxies, yet separated by expanses expanding faster than light. Even this analogy fails because inflationary space itself expands while generating new bubbles. It has no static scale, no boundary, no final size. But even inflationary bubbles may not represent the ultimate scale of existence, because some cosmological frameworks extend further still. String theory landscapes, higher dimensional brain cosmologies, quantum many-worlds branching. Each proposes structures larger than inflationary space alone. Thus, our journey outward continues, from bubble universes to the possibility of a multiverse containing fundamentally different realities across dimensions beyond spacetime itself. Chapter 14. The String Landscape. A multiverse of physical laws. As we continue outward beyond inflationary bubbles, beyond even the vast inflating substrate that may spawn universes endlessly, theoretical physics introduces an even deeper expansion of scale. Not merely more universes, but more possible realities. A framework where the laws of physics themselves can vary across cosmic domains. This concept emerges from one of the most ambitious theoretical efforts in modern science, string theory. String theory attempts to unify quantum mechanics and general relativity into a single framework describing all fundamental forces and particles. Instead of treating particles as point-like objects, string theory proposes that the fundamental constituents of reality are one-dimensional vibrating strings. Different vibrational modes correspond to different particles. Electrons, quarks, photons, and gravitons emerge as distinct oscillatory states of these strings. But for string theory's mathematics to remain self-consistent, it requires more spatial dimensions than the 3 we perceive. Most formulations require 10 total dimensions, with 9 spatial and 1 temporal. Some versions, such as M-theory, require 11. The extra dimensions are not extended like familiar space. They are compactified, curled into microscopic geometries at scales near the Planck length. The specific shape of these compact dimensions determines the physical properties of the universe. Particle masses, force strengths, symmetry groups, vacuum energy, all depend on the geometry of these hidden dimensions. And here scale expands again, because string theory does not predict a single allowed compactification geometry. It predicts an enormous number. Each geometry corresponds to a different vacuum state, a different set of physical laws. This collection of possible vacuum configurations is known as the string landscape. Estimates suggest the number of distinct stable vacua could be as high as 10 to the power of 500, a number so vast that it dwarfs any countable physical structure within a single universe. Each vacuum represents a possible universe with its own physical constants, its own particle physics, its own cosmological evolution. Some universes might have stronger gravity, others weaker electromagnetic interaction. Some might lack stable atoms entirely. Others might expand too rapidly for galaxies to form. Only a narrow subset would allow chemistry, stars, and complex structure. If eternal inflation operates within this landscape, then bubble universes may settle into different vacuum states as inflation ends locally. Thus each bubble would not only be spatially separate, it could obey different physical laws, different speed of light limits, different particle hierarchies, different dimensional compactifications. This framework expands the concept of size beyond spatial scale. It introduces parameter space scale, a multiverse defined not only by distance, but by diversity of physical possibility. Within the string landscape, universes may exist where proton stability differs, where nuclear fusion proceeds differently, where dark energy density prevents structure formation entirely. The anthropic principle arises naturally in this context. Observers exist only in universes compatible with observer formation. Thus, the physical constants we measure may represent selection bias rather than universal necessity. This interpretation remains debated. Some physicists view it as explanatory. Others regard it as philosophically unsatisfying without predictive falsifiability. Observational evidence for the string landscape remains indirect. String theory itself has not yet produced experimentally testable predictions accessible to current technology. However, certain cosmological signatures could hint at landscape physics, primordial gravitational waves from inflation, vacuum decay signatures, bubble collision imprints. All remain areas of investigation. Despite observational uncertainty, the string landscape provides a theoretical upper bound on structural diversity. If correct, the largest thing in existence may not be a spatial structure at all. It may be the total set of all possible vacuum states realized across an inflationary multiverse, a configuration space of universes, each with its own space-time, particles, and physical laws. Scale here becomes abstract rather than geometric, measured not in light years but in the number of possible physical realizations. To ground this idea, imagine each observable universe as a grain of sand. Inflationary bubbles form an ocean of such grains. The string landscape would represent not just the ocean but all possible oceans that could exist under different physical rules. A metastructure of potential existence. Within this framework, physical law itself becomes environmental rather than absolute. Gravity's strength may vary from bubble to bubble. Cosmic expansion rates may differ. Even dimensional structure could vary, with some universes possessing more extended spatial dimensions. Higher dimensional cosmological models suggest that our universe may be a three-dimensional brain embedded within a higher dimensional bulk. Other brains could exist parallel to ours, separated along extra dimensions rather than spatial distance. In such models, entire universes may coexist within higher dimensional space, interacting only gravitationally. These brain cosmologies expand structural scale yet again, from universes separated by inflationary expansion to universes separated by dimensional orientation. If true, the totality of existence becomes not merely vast in distance, but layered in dimensional complexity. Yet even this may not represent the final expansion of scale, because quantum mechanics introduces another possibility. One where universes multiply not only across space or dimensional configuration, but across branching quantum histories. A framework where every probabilistic outcome creates divergent realities, As we continue outward, scale transforms once more, from physical landscape to quantum multiplicity, where the largest structure is not defined by distance, dimension, or vacuum state, but by the total branching structure of reality itself. Chapter 15. The Quantum Many Worlds. Reality branching without end. As we continue outward beyond spatial scale, beyond inflationary bubbles, beyond the string landscape of possible physical laws, we enter a domain where size is no longer measured in light years, galaxies, or universes. Instead, scale emerges from probability, from quantum mechanics, from the fundamental uncertainty embedded within physical law itself. This is the domain of the many worlds interpretation, a theoretical framework proposing that reality continuously branches into multiple, equally real outcomes whenever quantum events occur. To understand this scale, we must begin with quantum mechanics itself. At microscopic levels, particles do not behave as classical objects. Electrons do not occupy precise positions until measured. Photons exist in superpositions of states. Quantum systems evolve according to wave functions, mathematical objects describing all possible states simultaneously. In standard interpretations of quantum mechanics, such as the Copenhagen interpretation, measurement collapses the wave function. A particle in superposition becomes one definite outcome. All other possibilities vanish. But the many worlds interpretation, first proposed by physicist Hugh Everett III in 1957, removes wave function collapse entirely. Instead, it proposes that all possible outcomes occur. Each measurement causes the universe's wave function to branch. Every quantum possibility becomes realized in separate, non-interacting branches of reality. When a photon passes through a beam splitter, it does not choose one path. The universe splits into branches where each outcome occurs. When a radioactive atom decays or does not decay, reality bifurcates. When any quantum interaction with multiple outcomes occurs, branching happens. And quantum interactions occur constantly. Every particle interaction, every chemical reaction, every photon absorption, every neuronal firing event. Branching occurs at unimaginable rates. Thus, the number of quantum branches grows exponentially over time. The many worlds interpretation does not add new physics equations. It simply takes the Schrödinger equation literally and universally. The wave function never collapses. It evolves continuously. All outcomes persist in superposed but decoherent branches. Decoherence plays a key role. Quantum branches do not interfere once environmental interactions entangle them with vast numbers of particles. This prevents observable cross-communication between branches. Each branch becomes effectively independent. Observers within a branch perceive a single outcome, but the full wave function contains all outcomes simultaneously. From this perspective, reality becomes a branching structure, not a single timeline, but a constantly diverging tree of histories. At every quantum decision point, the universe splits into multiple versions, some nearly identical, others diverging dramatically over time. The scale of this branching dwarfs even inflationary multiverses, because branching occurs not just once per universe, but continuously within each universe. Every inflationary bubble would contain its own branching many-world structure. Thus, multiplicity compounds. If inflation produces infinite universes, and each universe branches infinitely through quantum events, the total structure becomes unimaginably vast. But this branching does not occur across spatial separation. Branches coexist within Hilbert space, the abstract mathematical space of quantum states. They occupy the same underlying spacetime, but remain decohered and non-interacting. In this sense, they are parallel realities not separated by distance, but by quantum state. Every possible outcome of every event exists somewhere within the total wave function. Histories where stars formed differently, where galaxies merged earlier, where planetary systems varied, where life evolved along alternative biochemical pathways, all realized in separate branches. yet governed by the same fundamental quantum laws. One of the most profound implications of many worlds is that it removes randomness at the universal level. Quantum probabilities reflect branch weighting rather than indeterminacy. All outcomes occur. Observers experience probabilistic outcomes because they inhabit specific branches. But the full structure contains all possibilities. Experimental tests distinguishing many worlds from collapse interpretations remain difficult. Both predict identical observable results under most conditions. However, decoherence theory, quantum computing, and interference experiments support the idea that quantum superpositions persist rather than collapse intrinsically. Still, many worlds remains an interpretation rather than a confirmed empirical framework. Yet, if correct, it expands the scale of existence dramatically, because the largest thing would no longer be spatial, nor even cosmological. It would be the universal wave function itself, a mathematical structure encoding all possible quantum states across all branches. To ground this scale metaphorically, imagine shrinking our observable universe to a single grain of sand. Inflationary bubbles become oceans of such grains. The string landscape becomes countless oceans under different physical laws. The many-world structure would represent not oceans of grains, but every possible arrangement those grains could take across all histories. A combinatorial explosion of realities branching continuously, endlessly. But branching is not symmetric. Some branches carry far greater quantum amplitude. These correspond to highly probable outcomes. Others exist with vanishingly small amplitude, representing extremely unlikely configurations. Still, all exist within the wave function. The many-worlds interpretation reframes the question of largest structure. It is no longer a question of physical extent alone. It becomes a question of state-space extent. How many possible configurations of matter, energy, and spacetime can exist under quantum law? The answer approaches infinity. Because quantum systems with finite particles possess exponentially vast configuration spaces. Extend that to universal scale, and the branching structure becomes effectively boundless. Yet even this may not represent the ultimate expansion of scale, because some theoretical frameworks combine inflationary multiverses, string landscapes, and quantum branching into unified cosmological models. Structures where universes branch, vary in physical law, and proliferate across inflating spacetime simultaneously. In such frameworks, scale transcends any single axis of measurement. Spatial, dimensional, quantum, all expand concurrently. As our journey continues outward, we approach the final conceptual frontier. The totality of existence across all frameworks, all universes, all physical laws, all quantum branches, all dimensional layers. A structure so vast that even the term structure becomes inadequate, where the largest thing conceivable is not a physical object, but the complete set of all that exists or can exist under physical possibility. Chapter 16. The totality of physical reality, all universes, all laws, all branches. As our journey continues outward, scale ceases to expand in distance alone. It expands in category. We are no longer moving merely across larger regions of space, nor even across greater collections of universes. Instead, we are approaching the broadest scientifically grounded conception of existence itself, a framework that attempts to include every physically real domain described by modern theoretical physics. This is the totality of physical reality, the union of all universes produced by cosmic inflation, all vacuum states permitted by the string landscape, and all quantum branches generated through universal wave function evolution. To understand the magnitude of this totality, we must carefully assemble the layers we have already crossed. Each one represents not speculation detached from physics, but an extension derived from established theoretical frameworks. Cosmic inflation explains large-scale uniformity in structure formation. Eternal inflation arises naturally in many inflationary field models. String theory, though not empirically confirmed in full, emerges from mathematically consistent attempts to unify quantum field theory and gravity. The many worlds interpretation follows directly from the linearity of the Schrödinger equation when applied universally. Individually, each framework expands the scale of existence. Together, they produce a hierarchy that compounds magnitude beyond ordinary comprehension. Begin with inflationary space. Eternal inflation describes a background spacetime undergoing continuous exponential expansion. Within this inflating substrate, localized regions transition into lower energy states, forming bubble universes. Each bubble contains its own hot Big Bang, its own cosmic microwave background, its own structure formation history. These bubbles do not expand into external space. They form within the inflating medium itself, separated by distances that increase faster than light due to spacetime expansion. Within each bubble universe, physical constants may differ depending on how inflation ended locally. This leads directly into the string landscape. The compactification geometry of extra dimensions determines the vacuum state of a universe. Particle masses, force strengths, symmetry breaking scales, and vacuum energy all depend on this geometry. Thus, inflationary bubbles may populate different regions of the string landscape, each realizing a distinct set of physical laws. Inside each such universe, quantum mechanics operates. If the many worlds interpretation holds, then every quantum interaction generates branching histories. These branches do not separate spatially but exist within Hilbert space, the mathematical space of quantum states. Decoherence prevents cross-interaction, making each branch effectively autonomous from the perspective of observers within it. When these three frameworks are integrated, the resulting structure is vast beyond any prior category of size. Inflation produces potentially infinite universes. The string landscape allows each universe to possess different physical laws. Quantum branching multiplies histories within each universe continuously. The totality of physical reality, therefore, is not a single spatial structure. It is a layered, multidimensional ensemble combining space-time domains, vacuum configurations, and quantum state evolution. Its scale is measured not only in distance, but in possibility. To ground this concept scientifically, consider the role of Hilbert space. In quantum theory, the full state of a system is described by a wave function existing within Hilbert space. For small systems, this space is finite-dimensional. For macroscopic systems, its dimensionality becomes astronomically large. For an entire universe, the dimensionality becomes effectively incalculable. Each possible configuration of matter, energy, and field states corresponds to a distinct vector in Hilbert space. Quantum evolution traces trajectories through this space. Branching corresponds to decohered separations between trajectories. Now extend this to cosmology. Each inflationary bubble has its own universal wave function. Each vacuum state introduces different physical Hamiltonians governing evolution. Each quantum branch produces diverging cosmic histories. The totality of physical reality becomes the sum over all bubble wave functions, across all vacuum states, across all branching histories. It is not merely large. It is combinatorially vast. The number of quantum branches alone grows exponentially with time. Every particle interaction increases the dimensionality of the universal wave function's branching structure. Over billions of years, this branching produces an effectively unbounded multiplicity of histories. Combine that with the potential infinity of inflationary bubbles and the enormous count of string vacua, and the scale surpasses any numeric analogy grounded in familiar physical objects. Even terms like trillion, quadrillion, or googol lose descriptive power. We enter a regime where scale is defined by mathematical infinities and measure theory, rather than countable structure. Yet despite its enormity, This totality remains governed by physical law. Each domain evolves according to consistent internal dynamics. Inflation follows scalar field evolution equations. Vacuum states arise from string compactification solutions. Quantum branches evolve under unitary wave function propagation. The structure is vast but lawful, diverse but rule-governed. This raises a fundamental ontological question within physics. Does the totality of physical reality represent the largest thing that exists, or is it merely the largest structure permitted by our current theoretical frameworks? From a strictly physical standpoint, this totality encompasses all domains that can exist under known or hypothesized physical law. It includes all spacetime regions, all vacuum states, all quantum histories. There is no larger physical structure beyond it because it contains the full set of physically realizable states. But defining its size introduces conceptual challenges. Spatial measurement fails because many universes are causally disconnected. Dimensional measurement fails because extra-dimensional geometries differ between vacua. Temporal measurement fails because branching produces divergent timelines. Thus, its scale must be described abstractly. It is the configuration space of all physically instantiated realities. One way to conceptualize this is through phase space. In statistical mechanics, phase space describes all possible states of a system. Extend this concept to cosmology, and the totality of physical reality becomes the phase space of all universes, each evolving through its own trajectory. Another approach arises from path-integral formulations of quantum gravity. In these frameworks, reality is described by summing over all possible spacetime histories. Each history contributes to the universal wave function. The totality includes every physically allowed spacetime configuration weighted by quantum amplitude. Such formulations reinforce the idea that the largest physical structure is not a singular universe, but the ensemble of all universes permitted by physical law. Even cosmological measure problems emerge here. If infinite universes exist, how does one define probability across them? How does one compare the frequency of observers, physical constants, or cosmic histories? These questions remain unresolved in theoretical cosmology. They reflect the difficulty of reasoning about structures exceeding conventional scale. Yet observational cosmology still anchors this framework indirectly. Inflation is supported by cosmic microwave background anisotropy measurements. Large-scale structure distribution matches inflationary fluctuation predictions. Quantum decoherence is experimentally verified in laboratory systems. Thus, while the full multiversal totality remains unobservable, its foundational components rest on empirically supported physics. To ground its scale metaphorically, imagine shrinking our observable universe to a grain of sand. Inflationary space becomes an ocean filled with such grains. The string landscape introduces countless oceans, each governed by different physical rules. Quantum branching transforms each grain into an endlessly dividing fractal of histories. The totality of physical reality would then represent not the ocean, nor the grains, nor their branches, but the entire mathematical set containing all oceans, all grains, and all branching structures simultaneously. It is not a place. It is the full inventory of physical existence. Within it lie universes where stars formed earlier or later, where galaxies merged differently, where planetary systems varied, where life arose or did not arise, where cosmic expansion rates diverged. Yet all remain governed by internally consistent physical dynamics. But even here, our outward journey does not completely end, because physics itself raises one final frontier, a boundary where the definition of existence transitions from physical instantiation to mathematical possibility. Some physicists and philosophers propose that reality may not be limited to physically realized universes alone. Instead, all mathematically consistent structures may exist in some ontological sense. If so, the totality of physical reality may itself be a subset of something larger still. The space of all mathematically possible realities. Whether this represents physical existence or abstract description remains debated, but its scale would exceed even the multiversal totality we have described. Thus, as we prepare to move outward again, we leave behind the largest structure grounded in physical law. We approach the ultimate conceptual expansion of scale. From the totality of all universes to the totality of all possible structures describable by mathematics itself. Chapter 17. The Mathematical Universe, when size becomes pure possibility. As we move outward once more beyond the totality of all physically realized universes, beyond inflationary space, beyond string vacua, beyond quantum branching histories, the concept of largest thing undergoes its most profound transformation yet. We leave behind structures that exist in space-time. We leave behind universes governed by physical law. We even leave behind the requirement that something must be physically instantiated at all. Instead, we arrive at a hypothesis that pushes scale beyond physics and into ontology itself, the mathematical universe. This concept emerges most prominently from the work of physicist Max Tegmark, though its philosophical roots extend far deeper into the history of science and mathematics. At its core lies a radical proposal. Mathematical structures do not merely describe reality. They are reality. According to this framework, every mathematically consistent structure exists in the same ontological sense that our universe exists, not metaphorically, not symbolically, but literally. To understand the magnitude of this claim, we must begin with the role mathematics plays in physics. Every successful physical theory is expressed mathematically. General relativity describes gravity through differential geometry and tensor calculus. Quantum mechanics operates through Hilbert spaces and operator algebras. Electromagnetism emerges from Maxwell's equations. Particle physics arises from gauge symmetries and group theory. Time and again, mathematical formulations predict phenomena before they are observed. Black holes emerged from Einstein's equations before telescopic confirmation. Antimatter arose from Dirac's relativistic quantum equations before experimental detection. Gravitational waves were predicted a century before LIGO observed them directly. This predictive power suggests a deep correspondence between mathematics and physical reality. But the mathematical universe hypothesis takes a further step. If mathematics describes reality perfectly, perhaps reality is itself a mathematical structure, not made of matter but of relations, not composed of particles but of informational states governed by consistent rules. Within this view, our universe corresponds to one particular mathematical structure, a set of equations defining space-time geometry, quantum fields, and physical constants. But there are infinitely many other mathematically consistent structures, different dimensional geometries, alternative logical systems, distinct field interactions, universes governed by equations entirely unlike our own. If mathematical existence equals physical existence, then all such structures are equally real. Our universe is not unique. It is one element in the set of all mathematical realities. This framework is sometimes referred to as the Level 4 multiverse in Tegmark's classification. Level I corresponds to regions beyond our observable universe within the same space-time. Level 2 corresponds to inflationary bubble universes with different physical constants. Level 3 corresponds to quantum many-worlds branching. Level IV transcends them all. It includes every mathematically consistent structure. Its scale is not spatial. It is logical. It is the space of all possible formal systems capable of self-consistent definition. To grasp this magnitude, consider how many mathematical structures exist even within familiar domains. Euclidean geometry describes flat space. Non-Euclidean geometries describe curved spaces. Higher dimensional manifolds extend geometry beyond 3 spatial dimensions. Group theory defines symmetry operations across countless configurations. Topology describes connectivity independent of shape. Each mathematical framework defines its own internal reality. If all consistent structures exist, then universes may exist where space-time possesses 5 dimensions, or 11, or infinitely many. Others may lack space-time entirely, existing as purely relational networks. Some may obey deterministic laws, others probabilistic. Some may allow stable matter, others only transient energy patterns. Even logic itself may vary. Classical binary logic may be replaced by multi-valued or fuzzy logical systems. Causality may operate differently or not at all. Within the mathematical universe framework, any internally self-consistent structure qualifies as existent. This expands scale beyond enumeration. There is no largest number of universes, no finite set. The ensemble includes all structures describable by mathematics. Finite, infinite, continuous, discrete, deterministic, chaotic, each equally real within this ontological landscape. From within our own structure, we perceive physical law as fundamental. But from the level 4 perspective, physical law is local, a property of the mathematical structure we inhabit. Other structures possess different laws because their governing equations differ. This interpretation dissolves the distinction between physical possibility and mathematical consistency. If something can exist mathematically without contradiction, it exists physically in some domain. The implications for scale are absolute. The largest thing is no longer a universe, or a multiverse, or even a configuration space of universes. It is the totality of all mathematical structures, a domain not bound by space-time, energy, or dimensionality, but by logical consistency alone. Yet even this hypothesis invites scrutiny. One challenge lies in defining existence. Does mathematical consistency alone confer ontological reality, or is physical instantiation required? Platonist philosophies argue that mathematical forms exist independently of observers. Nominalist perspectives reject this, viewing mathematics as human abstraction. The mathematical universe adopts a radical Platonism. Mathematics is not discovered. It is existence itself. Another challenge involves measure. If all mathematical structures exist, how do we assign probability to observations? Why do we inhabit a universe with specific physical laws rather than others? Some proposals invoke observer self-selection. Conscious structures arise only in certain mathematical systems. Thus, observers inevitably find themselves within those systems. This echoes anthropic reasoning but extends it into mathematical ontology. Despite its speculative nature, the mathematical universe framework addresses deep questions. Why do physical laws exist? Why do mathematical equations describe reality so precisely? Why do certain constants permit structure formation? In this view, there is no single answer. All laws exist. All constants occur somewhere. Our universe is one realization among infinite mathematical possibilities. To ground its scale metaphorically, imagine shrinking our observable universe to a grain of sand. Inflationary multiverses become oceans of grains. String landscapes become countless oceans governed by different physics. Quantum branching multiplies each grain into infinite histories. The mathematical universe represents not the oceans nor the grains, but the entire library of all possible ocean types, grain compositions, and branching histories that can be described mathematically. Its size is not measurable. Its boundaries undefined. It contains every physically possible structure and every physically impossible one that remains mathematically consistent under alternate logical frameworks. Yet even here, our journey outward approaches its conceptual horizon. Because one final question remains. If all mathematical structures exist, what contains them? Is there a meta-framework in which mathematical existence itself resides? Or is mathematics the ultimate foundation beyond which scale cannot expand? In our next step, we approach this final boundary, the philosophical and physical limit of largest thing, where explanation itself encounters its outer edge, and where the question of scale transitions from structure to existence itself. Chapter 18. The Boundary of Explanation. Where scale meets the limits of knowing. As our journey continues outward, we arrive at a threshold unlike any we have crossed before. Up to this point, each expansion in scale has remained anchored, however loosely, to a framework of description. Stars could be measured, galaxies could be counted, filaments could be mapped. Even multiverses, whether inflationary or quantum, emerged from mathematical extensions of physical law, and the mathematical universe extended existence to the domain of all logically consistent structures. But now we approach a boundary where scale cannot simply expand by adding more distance, more universes, or more mathematical configurations. We approach the boundary of explanation itself. This boundary does not represent a physical edge. It is not a wall, nor a horizon defined by light travel time, nor a limit imposed by cosmic expansion. Instead, it is a conceptual frontier, a limit beyond which our current frameworks for describing reality begin to dissolve. It is the point where we ask not what is the largest thing that exists, but whether the concept of thing remains meaningful at all. To understand this boundary, we begin with a fundamental question in cosmology and philosophy. Why does anything exist rather than nothing? This question lies beneath every scale we have explored. Galaxies exist because gravity shapes matter. Universes exist because inflation ends locally. Mathematical structures exist because they are logically consistent. But why do the underlying laws, the logical structures, or the mathematical frameworks exist in the first place? At this depth, explanations risk circularity. Physical laws explain cosmic structure, but what explains physical laws? Mathematics describes physical law, but what explains mathematics? Some physicists propose that mathematical existence is self-necessary, that logical consistency alone guarantees existence. Others argue that mathematics requires a substrate, some meta-framework in which mathematical truths reside. But here explanation begins to thin, because any meta-framework requires its own justification. If mathematical structures exist within a meta-mathematical system, what explains that system? If physical reality emerges from quantum vacuum fluctuations, what explains the existence of the vacuum? If inflation emerges from scalar field potentials, what explains those fields? Each explanatory layer invites another deeper layer. This regress may be infinite, or it may terminate at a foundational principle beyond which explanation cannot proceed. Philosophers refer to this as the problem of ultimate grounding. Physics encounters it when probing Planck-scale reality. At distances of approximately 1.6 x 10^35 meters, quantum gravity effects dominate. Space-time itself becomes quantized or foam-like in many theoretical models. General relativity and quantum mechanics cease to integrate cleanly. String theory, loop quantum gravity, causal set theory, and other approaches attempt to describe this regime. But no theory has yet achieved empirical confirmation. Thus, our knowledge of the deepest physical substrate remains incomplete. Some models suggest space-time emerges from more fundamental informational or entropic structures. In holographic theories, space-time geometry arises from quantum entanglement patterns. The ADS-CFT correspondence demonstrates how gravitational dynamics in higher dimensional space can emerge from quantum field theories defined on lower dimensional boundaries. If such holographic principles extend universally, then space-time itself may not be fundamental. Instead, it could be emergent, a large-scale phenomenon arising from deeper informational relationships. If so, the scale of existence expands again, not outward in space but downward in fundamentality. Reality would consist of layers. Space-time emerging from entanglement. Entanglement emerging from quantum information emerging from mathematical relations, yet each layer invites the same question. Why that layer? Why those rules? Why that structure? At this boundary, explanation confronts epistemological limits. Human cognition evolved to interpret mid-scale environments. Objects meters in size, timescales of seconds and years, forces relevant to survival. Our intuitions strain at galactic scales and fail entirely at Planck or multiversal scales. Thus, our frameworks of explanation may be inherently constrained. We describe reality using mathematics because it is our most precise language. But mathematics itself may be an interpretive lens rather than ultimate ontology. Some philosophical frameworks propose that existence is fundamentally informational. Others propose that consciousness plays a role in defining reality. Still others maintain strict physicalism, rejecting non-empirical expansion beyond testable frameworks. But regardless of interpretation, the boundary we approach remains consistent. There is a limit to explanatory extension. Beyond it, questions remain meaningful, but answers become speculative or undefined. In cosmology, this boundary appears in multiple forms. The horizon beyond which we cannot observe, the Planck scale beyond which space-time description fails, the multiverse beyond which empirical testing becomes impossible, the mathematical totality beyond which ontology itself becomes abstract. These boundaries do not necessarily imply that reality ends. They imply that explanation encounters diminishing empirical traction. Science advances through testability. Hypotheses generate predictions. Predictions face observation. At sufficiently large or fundamental scales, observation becomes impossible in principle, not technologically limited but causally forbidden. Thus, certain domains of scale may remain forever theoretical, yet even this boundary possesses structure. Because explanations do not cease uniformly, they taper. Cosmic microwave background observations reveal early universe conditions, but not the Big Bang singularity itself. Gravitational wave astronomy probes compact object mergers, but not Planck-scale spacetime foam. Particle accelerators test quantum field interactions, but not unification at Planck energies. We observe edges of deeper realities without direct access. These edges form the epistemic horizon, the boundary of knowing. To ground this concept metaphorically, imagine exploring an infinite ocean. You map islands, continents, and currents. You infer deeper waters from tidal motion. But at some distance, fog obscures further mapping. You know the ocean continues. But direct observation fails. The boundary of explanation is that fog. It does not define the edge of reality. It defines the edge of current intelligibility. Yet even here, scale retains meaning. Because the boundary itself encompasses all explanatory frameworks. Everything we can describe, everything physics can model, everything mathematics can formalize. It is the largest domain of structured understanding. Beyond it lies unformalized possibility, unknown unknowns, structures that may exist but remain beyond articulation. Thus, the largest thing we can meaningfully describe may not be the mathematical universe alone. It may be the total domain of explainable existence. All realities accessible to logical, mathematical, or empirical description. Whether this domain has limits remains uncertain. Some argue that Gödel's incompleteness theorems imply that any sufficiently powerful formal system contains truths it cannot prove internally. If so, then explanatory systems themselves possess intrinsic limits. No single framework can capture all truths. Reality may exceed any formal description. Thus, scale transcends even mathematics. It enters the domain of meta-reality, the totality of what exists, describable or not. As our journey prepares to move outward one final time, we approach the outermost conceptual horizon. Not a structure, not a multiverse, not even a mathematical ensemble, but the ultimate abstraction, the set of all existence and all possibility, the largest conceivable thing if the word still applies, where scale no longer expands through addition, but through the dissolution of boundaries themselves. Chapter 19. The total set of all existence, where scale dissolves entirely. As our journey continues outward, we arrive at the furthest conceptual horizon reachable through structured reasoning. We have crossed stars, galaxies, clusters, superclusters, filaments, walls, and the cosmic web. We have expanded beyond the observable universe into the total universe, then beyond into inflationary multiverses, string landscapes, and quantum branching realities. We have entered the domain of all mathematically consistent structures, and then approached the boundary of explanation itself. Now we arrive at the final conceptual expansion of scale that can be meaningfully articulated, the total set of all existence. This is not a structure in space-time. It is not bound by physical law, nor by mathematical formalism alone. It is the conceptual aggregation of everything that exists, has existed, will exist, or can exist in any definable sense. To understand this scale, we must begin by clarifying the transition that occurs here. Up to the mathematical universe framework, scale expanded by including more structures within a shared ontological category. All mathematically consistent systems were granted existence. That expansion was still grounded in logical coherence. It required internal consistency. Contradictory systems were excluded. But the total set of all existence removes even that boundary. It includes every form of being, regardless of whether its governing principles are mathematically expressible, physically instantiated, logically formalized, or currently comprehensible. This totality contains all universes, all multiverses, all branching histories, all dimensional structures, all informational substrates, all emergent realities, and all frameworks that may lie beyond our capacity to define. It is not simply large, it is categorically complete. To approach this idea carefully, we can examine how each previous expansion added a layer of inclusion. The observable universe included all matter and energy accessible through light. The total universe extended beyond observation to include all space-time regions. Inflationary cosmology expanded scale to include multiple universes formed through scalar field dynamics. The string landscape expanded it further to include universes governed by different physical constants. Quantum many-worlds introduced multiplicity of histories within each universe. The mathematical universe extended existence to all mathematically consistent structures. But each of these still relied on definable frameworks. They operated within physics or mathematics. The total set of all existence includes every such framework simultaneously. It also includes any frameworks not yet conceived, any ontological category that could host existence, whether describable through mathematics, logic, information theory, or other unknown structures. At this scale, the word thing begins to lose conventional meaning, because a thing implies boundary, identity, and distinction. The total set contains all distinctions. It cannot be bounded by anything external, because there is nothing external to it. It cannot be measured, because measurement requires comparison. It cannot be located, because location requires space-time reference. Thus its scale is absolute. It is the largest conceivable totality not by size, but by completeness. Philosophically, this concept intersects with metaphysical frameworks across cultures and eras. In classical ontology, it resembles the idea of being itself, the sum total of all that is. In set theory, one might attempt to describe it as the set of all sets, though such constructions generate paradoxes within standard axiomatic systems like Zermelo-Frankel set theory. Russell's paradox demonstrated that naively defining a set containing all sets leads to logical contradiction. Thus even formal mathematics resists fully containing total existence within a single definable structure. Some approaches circumvent this through hierarchical set universes or category theory frameworks. But even these remain abstractions rather than ontological claims. From a physical standpoint, cosmology does not require such a totality to function. Observational science operates within measurable domains, yet theoretical expansion inevitably points toward the question of total inclusion. If multiple universes exist, what contains them? If mathematical structures exist, what defines their collective ontology? If explanation has limits, what lies beyond explanation? The total set of all existence becomes the conceptual terminus of such questioning. It includes physical realities and abstract realities, realized structures and unrealized possibilities, known frameworks and unknown frameworks. Yet describing it introduces linguistic tension. Language relies on differentiation, subject and object, inside and outside, part and whole. The total set of all existence dissolves such distinctions. It is not inside anything. It has no outside. It contains all wholes and all parts simultaneously. In this sense, its scale is not additive but integrative, not a sum of pieces, but the absolute inclusion of all categories of being. To ground this in metaphor, imagine every structure we have explored as concentric expansions. Stars within galaxies, galaxies within clusters, clusters within superclusters, superclusters within filaments, filaments within the cosmic web, the web within the observable universe within the total universe within inflationary multiverses, multiverses within the mathematical landscape. The total set of all existence is not another outer ring. It is the entire diagram simultaneously. Every ring, every layer, every possible extension, contained without exclusion. One might ask whether this totality can change. If it contains all existence across time, then it includes all past, present, and future states. If time itself is emergent, then temporal change exists within it, but does not alter its completeness. Thus, it is temporally inclusive as well. Another question arises regarding necessity versus contingency. Is the total set of all existence necessary? Must it exist? Or is its existence contingent upon deeper principles? At this level, such distinctions blur. Necessity presumes logical structure. Contingency presumes alternative possibility. The total set includes all logical structures and all possibilities simultaneously. Thus, necessity and contingency coexist within it as internal properties rather than external conditions. The total set of all existence also reframes scale psychologically. Human cognition struggles with astronomical numbers. Trillions of galaxies challenge imagination. Infinite universes exceed it, but completeness transcends quantity entirely. It is not about counting, it is about inclusion. Everything that exists belongs to it by definition. Thus its size cannot be described through magnitude alone. It is maximal by definition. There is nothing larger because there is nothing outside it. Yet even here, one final conceptual step remains. A question that arises naturally once totality is defined. If the total set of all existence includes all realities, all frameworks, all possibilities, does it include its own description? Does it contain the structures that attempt to understand it, the observers within universes, the theories they construct, the language they use, the very narrative unfolding now? If so, then scale loops inward as well as outward. Existence contains observers who attempt to comprehend existence. The largest thing contains reflections of itself at smaller scales, conscious systems modeling the totality from within. This recursive property introduces the final conceptual expansion, where scale does not extend further outward, but turns inward through self-reference, toward the role of observation, awareness, and cognition within the largest structure that can exist. And as we move into the final chapter, we approach that reflective horizon, where the universe, the multiverse, the mathematical totality, and the set of all existence become aware of themselves through the minds that arise within them. Chapter 20. the reflective horizon, where the largest structure becomes aware. As our journey reaches its final expansion, scale no longer stretches outward into larger distances, larger universes, or larger frameworks of existence. Instead, scale turns inward. We arrive at the reflective horizon, the point at which the largest conceivable structure, the total set of all existence, contains within itself systems capable of observing, modeling, and contemplating that very totality. This is the final transformation in our exploration of the largest things in the universe. Not a transformation of size, but of perspective, because once observers emerge within existence, scale acquires a new dimension: self-awareness. To understand this horizon, we begin with a biological foundation. Conscious observers arise through evolutionary processes within particular cosmic environments. Stars forge heavy elements through nuclear fusion. Supernovae distribute those elements into interstellar space. Planetary systems form from enriched molecular clouds. On certain worlds, chemistry organizes into self-replicating systems. Biological evolution produces increasingly complex neural architectures. Eventually, cognitive systems arise capable of abstraction, mathematics, and cosmological modeling. Thus, consciousness emerges as a late-stage product of cosmic evolution. It depends on stellar nucleosynthesis, planetary stability, chemical complexity, and evolutionary selection. Observers are therefore not external to cosmic structure, they are embedded within it. The atoms forming neurons were forged in ancient stars. The laws governing synaptic transmission arise from electromagnetic interactions defined by physical constants shaped by early universe conditions. Even cognition is constrained by quantum mechanics, thermodynamics, and information processing limits. Thus, when conscious beings contemplate the universe is, in a very literal sense, contemplating itself. Carl Sagan expressed this poetically when he described humans as a way for the cosmos to know itself. From a scientific standpoint, this statement reflects emergent complexity. Systems capable of modeling their environment arise from that environment's physical processes, but when those models extend to cosmic scale, something extraordinary occurs. The largest structure known becomes represented within localized cognitive systems. Neural networks containing billions of neurons construct conceptual representations of galaxies, multiverses, and mathematical totalities. These representations are not physically large. They occupy small regions of biological tissue. Yet, informationally, they encode models of immense scale. This introduces a new dimension of largeness. Informational scale. The largest physical structures exist across vast space-time domains, but the largest informational structures may exist within cognitive or computational systems modeling those domains. Human cosmology is one example. Through observation, mathematics, and simulation, scientists construct models of cosmic structure extending billions of light years. Computers simulate galaxy formation across cosmic time. The cosmic microwave background is mapped at high precision. Quantum field theories describe particle interactions at subatomic scales. Thus, localized systems encode information spanning extremes of size. In this sense, the reflective horizon marks the convergence of outer and inner scale. The universe produces observers. Observers model the universe. The model contains representations of the totality that produce the observer. This recursive loop introduces self-reference into cosmic structure, and self-reference carries profound implications. In mathematics, self-referential systems give rise to Gödel's incompleteness theorems. Any sufficiently powerful formal system contains true statements it cannot prove internally. Applied metaphorically to cosmology, observers within the universe may never fully model the totality they inhabit. Their frameworks may approach completeness asymptotically but never achieve it fully. This aligns with the epistemic boundaries discussed previously. Observation is limited by light speed. Theory is constrained by testability. Cognition is bounded by neural architecture and information processing capacity. Yet despite these limits, observers extend comprehension farther than any other known system. No galaxy models itself. No cluster simulates its own formation, but conscious systems do. This introduces a unique structural layer within the total set of all existence. Reflective systems, entities capable of representing, analyzing, and interpreting the structures from which they emerge. From a thermodynamic perspective, this reflection is costly. Cognitive systems require energy gradients. They depend on stellar output, planetary environments, and biological metabolism. Information processing increases entropy globally even as it generates local order. Thus, the reflective horizon is also a thermodynamic phenomenon. Awareness arises in regions where energy flows permit complex organization. From an evolutionary standpoint, cognitive modeling confers survival advantage. Predictive brains navigate environments more effectively. But cosmological modeling extends far beyond survival necessity. It represents curiosity-driven abstraction, the drive to understand origins, scale, and structure. This drive has produced telescopes, particle accelerators, gravitational wave detectors, and deep space observatories. Each instrument extends the reflective capacity of consciousness outward. We build machines that observe galaxies billions of light-years away, detectors that measure space-time ripples from black hole mergers, satellites that map relic radiation from the early universe. Thus, reflection becomes technologically amplified. The universe not only becomes aware through biological observers, it becomes instrumentally aware through technological extensions of cognition. Computational cosmology simulates universes. Quantum computers may one day simulate quantum field evolution at unprecedented scales. Artificial intelligence systems analyze cosmic survey data beyond human processing limits. Thus, reflective capacity expands beyond biological constraint. Yet reflection remains embedded. No observer stands outside existence to view it wholly. All models are internal representations constructed from within. The reflective horizon, therefore, marks both the culmination and the limitation of scale comprehension. It is where the largest structure becomes representable, but never fully observable. Where totality becomes conceivable, but never exhaustively knowable. Philosophically, this introduces reflexivity into ontology. Existence contains observers. Observers construct models of existence. Those models include observers constructing models, an infinite regress of reflection nested within the total set. Some cosmological thinkers propose that this reflexivity may be fundamental. John Wheeler's participatory anthropic principle suggested that observers play a role in bringing the universe into definable being through measurement. While speculative, such ideas emphasize the deep entanglement between observation and reality description. Even within standard physics, measurement plays a critical role. Quantum systems require interaction to produce definite outcomes within observer frameworks. Cosmic parameters become meaningful only through observational inference. Thus, reflection is not peripheral. It is central to how existence becomes articulated. To ground this final scale metaphorically, imagine again the concentric expansions we traced. Stars within galaxies, galaxies within clusters, clusters within superclusters, superclusters within filaments, filaments within the cosmic web, the web within universes, universes within multiverses, multiverses within mathematical structures, mathematical structures within the total set of all existence. Now add one final layer. Observers within existence constructing models of all prior layers. The diagram folds inward. The outermost ring contains minds that hold the entire diagram within conceptual space. This is the reflective horizon, the final expansion of largeness, where scale is no longer measured by distance, number, or inclusion alone, but by awareness. The largest structure becomes self-aware through the observers it generates. And as our journey concludes, the hierarchy of the largest things resolves into a unified vision. From stellar titans to cosmic webs, from universes to multiverses, from mathematical totalities to existential completeness, all culminating in the realization that the act of understanding itself is part of the structure being understood. The universe expanding outward in space and inward through awareness. The largest thing that exists is not only the totality of all existence, it is the totality aware of itself through the minds that arise within it. And here, at the reflective horizon, our exploration of the largest things in the universe reaches its final boundary. Not an edge of space, but an edge of comprehension, where scale, structure, and awareness converge into a single immeasurable whole, outro, the long descent home. And so our journey comes to its quiet end. We began with a single point of light, a star so large it could swallow the orbit of Saturn, a hypergiant whose surface churned with convection cells larger than solar systems, whose life would end in a supernova bright enough to outshine an entire galaxy. From that first step, scale began to loosen its grip on familiarity. We moved outward to stellar nurseries, vast molecular oceans where gravity gathered cold hydrogen into the seeds of suns. Regions where thousands of stars ignited at once, illuminating their birth clouds like lanterns in cosmic fog. From there, galaxies emerged, island universes of hundreds of billions of stars, rotating through darkness across spans so wide that light itself required 100,000 years to cross them. We crossed spiral arms, galactic halos, supermassive black holes anchoring stellar cities, then galaxies gathered into clusters. Continents of light bound within gravitational basins filled with superheated gas and dark matter halos. Structures millions of light years wide, where galaxies orbited one another over billions of years. Clusters gathered into superclusters. Superclusters aligned into filaments. Filaments formed walls. Walls assembled into the cosmic web, a universe-scale lattice of matter stretching across billions of light years, where galaxies traced the threads of dark matter scaffolding laid down in the earliest moments after the Big Bang. We reached the observable universe, a sphere 93 billion light-years wide, containing trillions of galaxies and more stars than grains of sand on Earth. Yet even that vastness was not the end. Beyond it lay regions forever unreachable by light. The total universe extended further still. Inflationary space expanded the scale again, spawning bubble universes across an eternally inflating substrate. String landscapes multiplied physical law itself, allowing universes governed by entirely different constants and forces. Quantum branching multiplied histories within each universe, producing an ever-diverging tree of realities. Mathematical structures expanded existence beyond physics, proposing that every logically consistent system exists. And then we crossed the boundary of explanation, where knowledge itself encounters its horizon. Finally, we arrived at the total set of all existence, the absolute inclusion of everything that is, has been, or can be. And there, at the reflective horizon, we discovered something unexpected, that the largest structure in existence contains observers capable of modeling that very structure, that awareness itself is woven into the fabric of scale, that the universe, through minds like ours, becomes capable of contemplating its own immensity. Now, as this long descent home begins, scale contracts once more, from total existence back to the observable universe. From the observable universe back to the cosmic web, from the web back to galaxies, from galaxies back to stars, and from stars back to a single world orbiting a single sun. Perspective shifts as we return, because nothing around you has grown smaller. Mountains remain tall, oceans remain vast, cities remain sprawling. Yet against the hierarchy we have crossed, they feel gentler, quieter, more intimate. The night sky, when seen again, may no longer appear as scattered points of light. It may appear layered, stars as neighbors, galaxies as distant cities, filaments as hidden architecture. each point overhead belonging to a structure far larger than sight alone reveals. And yet, within all that immensity, something fragile persists, a narrow band of planetary conditions capable of supporting life. A thin biosphere sustained by stellar warmth, a species capable of curiosity, of building telescopes, of mapping cosmic radiation, of asking how large existence truly is. This duality defines our place in scale. We are small in physical size, yet large in reflective capacity, composed of atoms forged in ancient stars, arranged into neural systems capable of modeling cosmic evolution across billions of years. We are both insignificant and extraordinary, a fleeting biological phenomenon and a reflective aperture through which the universe examines itself. As the night deepens and rest draws nearer, the hierarchy we have traveled may begin to soften. Numbers fade, distances dissolve, structures blur into impression rather than measurement, but the feeling of scale remains, a quiet awareness of immensity. Not overwhelming, but expansive. The realization that existence is vast beyond comprehension, and yet, in this moment, contained within the quiet rhythm of breath. The universe stretches across billions of light years, but it is also present in the warmth of starlight reaching Earth tonight, in the photons that left distant suns before human civilization began, in the cosmic microwave background still whispering from the universe's earliest epoch, in the atoms within your body formed in stellar cores long extinguished. You are not separate from scale. You are composed of it, a localized arrangement of cosmic history capable of awareness, and so the journey outward becomes a journey inward as well, from galaxies to consciousness, from structure to reflection, from immensity to presence. If you have topic ideas you would like explored in future midnight lessons, place them in the comments below. Your curiosity continues to guide these voyages across knowledge, scale, and time. For now, allow the mind to rest. Let the distances drift away. Let the structures dissolve into quiet starlight. The largest things in the universe remain vast, silent, and ever-expanding. But here, at the close of this journey, scale settles into stillness, and the cosmos, immeasurable and infinite in its reach, grows calm enough to sleep within.